Vill du att jag kollar? Vi väntar tills klockan är 15:15 innan vi börjar på riktigt. Det är viktigt.
Ni kör med akademisk kvart där. Ja. Det har inte vi här uppe.
Min klocka är mer än 15 redan.
Okay.
Kalle? Den är, ja, jag går efter den, men okej. So if we agree that the time is 9:15, we may as well start. So I wish you all welcome to the act of defending the thesis, The Fight on the Flights, Emergency Evacuation, Human Physiological Performance, Leg Muscle Activity, and Gait Biomechanics during Exhaustive Stair and Slope Ascent.
Exactly.
My name is Gudbjörga Erlingsdotter. I am an associated professor here at the Department of Design Sciences, and I have been appointed by the Faculty of Engineering to be the chairman of the Defense Act. What this means in practice is that I will provide you with information about the main actors, guide you through the act, and make sure that the required formalities are met. So let me begin with introducing the two main actors of today's defense. So first, the respondent, Amitava Halder, technology licentiate in working environment. He will be defending his thesis, The Fight on the Flights, Emergency Evacuations, Human Physiological Performance, Leg Muscle Activity, and Gait Biometrics during Exhaustive Stair and Slope Ascent.
Yep.
The opposition of the thesis will be carried out by Dr. Denise McGrath, University College Dublin, Ireland, who has been appointed by the Faculty of Engineering. Dr. McGrath has considerable experience working at the interface of healthcare, industry, academia, and community groups in the creation of connected health-based solutions. Through research in the sporting domain, she has understanding of innovative technologies and analysis of techniques applied to investigating movement in humans and horses, with the ultimate goal of enhancing sport performance. I hope this is right, Denise.
Yeah.
Okay, so next we have the examination committee. First, Professor Ola Eiken, Environmental Physiology, KTH, Stockholm. Can we get a wave? He waved. Okay.
Yeah.
Then we have Dr. Hilde Færevik, Department of Health Research, SINTEF, Trondheim, Norway. And Professor Christer Malm, Department of Community Medicine and Rehabilitation, Umeå University, Umeå. Then we have the examination committee member as the deputy member, Associate Professor Stefan Svensson, Swedish Civil Contingency Agency, MSB, Revinge. Lastly, we have Amitava's supervisors. We start with Amitava's main supervisor, Associate Professor Xiaoxi Gao. Then co-supervisor, Associate Professor Kalev Kuklana. Institute for Safety, Sotermer, the Netherlands. Are you there, Caleb? Yeah.
Yes, I am.
Yeah. And co-supervisor, senior lecturer Michael Miller, Department of Health Science, Lund University. And now we have reached the procedure of the Defence Act. The respondent, Amitava, will be given the opportunity to present erratas to the published thesis. After that, Amitava will present his thesis.
Yep.
After that, Dr. McGrath will make a short overview of the scientific area and will put the thesis in the context of international research. Thereafter, we will have a short break, about 5 minutes, and those of you who do not have the possibility or interest to stay for the whole defense can leave, and the rest of you can stretch your legs. After the break, we'll start with questions and discussion between opponent and respondent.
Yep.
When they are finished, we will proceed with questions from the members of the examination board and deputy member. Then there will be time for questions from the audience, both in place and on YouTube. The audience on YouTube can mail their questions to my mail address. It's written on the whiteboard, and I think it's on YouTube too. Yeah. After all questions have been asked and answered, hopefully, we will close the Defence Act. So, Amitava,
Okay.
please, the floor is yours.
Thank you, Honorable Chairperson. I'm very glad to see some of you here within this crisis period. I know many of my friends and their eyes are on me right now on YouTube. And I'd like to thank to the department for arranging these techniques, which is allowing me to reach there, reaching my research to them, and especially connecting the most important people, my opponents, Dr. McGrath from Ireland, Professor Aiken from Stockholm, Professor Malm from Umeå, and Dr. Hilde Færvik from Norway. Welcome everyone to my presentation, The Fight on the Flights, Emergency Evacuation, Human Physiological Performance, Leg Muscle Activity, and Gait Biomechanics during stair and slope ascent. I think you have already got the word fight here. I meant the human capacity required during ascent on the stair flights. So why we need that? Why stair ascending capacity needs to be evaluated? There's a current trend to build deep underground structure all over the world, and Sweden is not an exception when there's a gradual demand of transportation. And Sweden is now currently building a deep bus stop as well. And there will be one of the deepest subway in the world in Stockholm. And we don't need to go to Stockholm. The day I nailed the thesis, I have found this piece of news in the Sydsvenskan, the local newspaper. Lund Central will be the biggest underground railway station in Sweden. And there will be a tunnel from north of Lund to south of Lund. So there's a possibility to have many underground long stairs. And if we look back to my homeland, where I born, in Dhaka, so she's going to have her first ever subway, around 238 kilometer long underground, with 52 stations. So there's a possibility to have many underground facilities. So if something happens, like it happened in 2017 in Russia, the second largest city in Russia, St. Petersburg. I'm talking about the terror attack, which left 11 dead and 52 injured. I don't expect something will happen here, but if. So there was a required to evacuate as quick as possible. They need to evacuate the station as early as possible. So are we ready? Are we prepared? So what capacities are required? So in this research, we have tried to understand what constrains our performance. Is it cardiorespiratory capacity, or is it local muscle fatigue, or which one comes first? So this combined method in this evacuation field, we have tried to identify two human performance constraints during estuary ascent. So I had two-fold aim. One is physiological, another one is biomechanical. So in the first aspect, we wanted to explore and compare the estuary ascent physiological constraints and capacities required during estuary ascent at a self-preferred pace when you climb at your preferred chosen pace. And also we have done this on a different machine control paces on the stair machine. So self-preferred pace should be the left figure, longest stairs, and we've done the machine control pace in the laboratory. And the second aspect is biomechanical. So we wanted to see what happens when someone is fatigued. So we wanted to explore and compare the effects of fatigue on gait biomechanics on a slope surface when you walk upward. So what are the research questions? So I have also divided the research questions in, I have 5 handful research questions, and also they were divided into these two aspects, physiological and biomechanical. And first one is self-preferred pace and also comparing different machine control pace as well. So this is question number 1. What are the required cardiorespiratory capacities and limitations during estuary ascent? Number 2 is the leg muscle. How do the leg muscle performs and what are the limitations? Number 3, so we need to identify the step rates when someone is climbing on a stair machine. So we need a model and we need to calculate the step rates based on individual physiological capacity. So so we wanted to see how can the different step rates can be estimated based on individual physiological capacity, and how can the ascending duration and height be predicted by the physiological model. Number 4, we wanted to see how can the leg muscle activity and fatigue can be interpreted by a model using electromyography data. And number 5, the last one, based on a biomechanical aspect, we wanted to see our physical exhaustion and local muscle fatigue of the legs, the potential risk when walking up an inclined surface. So how did we get the data? How did we do this? How did we get this answer of these questions? So we had different studies, around 4 years, and I have divided these all studies in 3 phases. First phase was based on the field studies. We have done 3 field studies. We have chosen 3 different heights of buildings. One is 13th floor building here, might have been this Lund one, and this Kista Tower in Stockholm, and the current deepest tower in Stockholm in Västerskogen. So this gives, here people climbed in the self-preferred pace. And then it gives paper 1. And then in the second phase, we had the lab study. We calculated 3 different step rates based on the individual physiological capacity at 60%, 75%, and 90% of VO2 max speed on the stair machine. And then it gives paper number 2. And combine this first phase and second phase, we got paper number 3, that is physiological evacuation model. And the last phase, we wanted to look at if someone is climbing at maximal effort, how long they can last. So we wanted to know the endurance and the height and duration as well. So this is 100% maximal, 100% of view to max speed on the stair machine. And the second part of this last phase, we looked at the walking gait when someone is fatigued. So these are the 5 papers. 3 of them are published. You can find them in page number 15 in the book. And paper number 4, I have submitted the second revision. I thought it will be accepted, but it's not yet. And paper number 5, this biomechanical part, this is the second part of the last phase of a study. This is submitted in March, is under review still. So 3 published in international journals and 2 are under review right now. So what instruments did we use? I have also divided them in a 2 phase as well. The first and second phase we collected oxygen uptake data using the Cortex MetaMax, and also heart rate based on from Polar, and then climbing speed on the regular stairways in the buildings. These 3 we use camera to record the ascending speed, and muscle activity using the EMG from Finland, and definitely we use Borg scale to know the perceived exertion. And this last phase, we had a new MetaMax that we use for collecting oxygen uptake to know the ascending endurance until exhaustion. And we had also similarly polar heart rate, and also we measure lactate to know the fatigue level, and also the Borg scale to know the subjective perceived exertion. And the last part of the last phase, we had this walking gait biomechanics. In order to do that, we had to arrange a synchronized system based on motion captured cameras. We had 8 cameras, EMG and force plate, to record ground reaction forces. We had to synchronize all 3 of them to record walking and to get the time synchronized data. That was quite challenging, but we managed it somehow. And we selected several muscles from the legs, dominant leg muscles. We have had 6 muscles, but we have measured 4 muscles in a study. We have chosen 3 muscles from the thigh, 2 calf muscles, and 1 anterior leg muscles. But we haven't used all 6 at the same time, 4 of them in each phase. Well, let's take a look at the answers. What you got? The first one is the cardiorespiratory capacity and limitations. So let's take a look at the self-preferred phase. From the paper 1, we had this oxygen uptake average figures for all subjects here. And from y-axis, you can see the oxygen uptake level, milliliter kg per minute. And x-axis, the time normalized period. So average time duration was here for about 8 minutes. And you see here about 30 to 40% time. That means more than around 3 minutes. We got a stable state of VO2 values. And people have managed to climb until end. So you see that they have managed. So no one has stopped and all the way down. So there's a stable state oxygen uptake required to reach to the top of the floor. And if we look at the lab study, I'm giving some examples from 90% level here, and you see it was about average duration was about 4.3 minutes. So it is 4.3 minutes here, and then oxygen uptake here. So we see around end of the ascending, we got some stable values. compared to 100% level, here the total duration is 3.5 minutes, so 3.5 minutes. And you see here, oxygen uptake was quite stable at the end, but yeah, so usually it takes 2 to 3 minutes to get a stable values. But I would like to give the example of 75% level that we had from the lab. Here we can see, I'm giving this one to compare with the field study. So we had 100% level here, but in the 75%, you see the oxygen uptake level about 38 milliliter kg per minute. And this is quite equivalent to the field study when you asked them to choose their speed to climb. So it's quite similar. So lab study showed that from the field study, it was around 75% level that people have chosen their capacity. They haven't taken the 100% level. So it is about 47, 48 milliliter kg per minute. So they haven't taken the maximum level. So intensity of the self-preferred pace was equal to 75, what we can say from here. So we don't see, we cannot say that people have chosen their maximum speed. So this is in, we have reported in paper 1, 2, and 4. So if we look at the muscle activities, we need two different parameters, amplitudes and frequency. So left column is the amplitudes, and we have 4 muscles here. And the so y-axis, left y-axis, and right y-axis, we have this ascending speed. So we record the ascending speed from the camera. This is this one, this straight line without any dots. And these are the 4 muscles. We see a nice correlation between this ascending speed and the 4 muscles. So in the beginning, subject thought we can go at maximum high speed, but with the time, we see there's a sharp decline in here, then continued as the speed was manageable until the end. And we can see the frequency here, they're almost similar. It was not changed at all compared to the ascending speed. So they have managed with the same frequency, they have continued the same speed. They haven't tried to go in a higher speed later on as well. So what we can say from this result, so decreased amplitude and unchanged frequency, we could say muscle force or power decrease. So they didn't try to go, it was not possible to maintain all the time high speed. I will come to this model that we have developed to interpret more later on. So this was from the self-preferred pace. And if we look at the control, this is also paper 1, sorry. And then if we look at the machine control pace at 100% VO2 max, we just saw the amplitudes were decreased, and in comparison here, you see that all the amplitudes were increasing until the end. So there are more muscles were recruiting all the way to reach until they were fatigued. And if you look at the frequencies are here, then they have just two of the muscles were decreased here. So these two, one thigh muscle and one anterior leg muscle were significantly decreased compared to the other two, one calf and one other thigh muscle. So if we have this increased amplitude and decreased or unchanged frequency, we can say muscle fatigue based on our model. Increased amplitude and decreased frequency. I will describe more in the model later on. So this is, we have this paper number 4 at maximum 100% level, but 60, 75, and 90% level are in paper number 2. So paper number, research question number 3. So we have developed the model that helped to estimate our step rate. So we have developed 3 equations. First one, to calculate the step rate, it was developed from the field study and also the large database from Norway. We have used that one and used statistics to get this formula. And we can use this one to calculate any step rate if we know someone's oxygen uptake, a maximum individual work capacity. But in the 100% level, when you do the maximal effort, we don't need this calculation. We can do this one, this formula that is based on the stair machine step height and width. So sometimes maybe a step height can be difficult, different between the staircase. So we also have developed another one, vertical displacement. How high can we ascend per minute? So that is, we can use this one to calculate the vertical displacement as well. So these are described in paper number 3 and paper number 4. Yeah, this is the model we have developed. I named it muscle activity interpretation square. So idea is to we need two different things, amplitudes and frequency. So I thought, how can this be combined together? So this is the equation is given here, and this is combined amplitude and frequency to get the one point that I named mark, muscle activity rate change. So how we did it? So the changes between each, so we had a time normalized period for whole duration here, let's say, and how the changes between frequency from 10% to 20% until end, and similarly amplitudes from 10 to 100%. So you combine these changes to get 1 point as a mark. So these we have in the paper 1, 2, and 4. So I'm going to give an example from the self-preferred pace, and we have taken the thigh muscle, and you see, if you remember from the field study, subjects didn't choose their maximum speed all the time, so you don't see any pattern here. They were scattered in different parts of the square: recovery, muscle fatigue, muscle force increase, muscle force decrease, muscle fatigue here in the right lower box. And similar to the 31 floor building, so you don't see any common pattern. They were scattered in different boxes. But if we look at the machine control pace, we have found when all these mark points are scattered here in the muscle fatigue square, because we know that they have reached the fatigue level. So it showed based on the mark points here. Similarly, at 100% level, we see muscle fatigue. So this model supports the individual estimation from the amplitudes and median frequency as well. So this one we have paper 4, and this paper 3, and this is paper number 1 from the field studies. Now the last part of the last phase, gait biomechanics. So we want to see how fatigue affects our walking gait. So we have found the decreased ground reaction forces during heel strike. So we have got the forces during the one stance phase. So we found these ground reaction forces decreased during heel strike and toe off as well. And an increased coefficient of friction was required to maintain balance and for the gait stability in order to prevent any slips and fall accidents. And similarly, we have seen the decreased peak and minimum foot absolute angle during heel strike and toe off as well. So we can see there's an altered gait biomechanics due to fatigue and exhaustion. So these we have only paper number 5, the last part of the study. Yeah, so I'm going to give some highlights. I have 8 highlights on the 8th of May. First one, if we think about regarding an emergency all-out effort, we have found that intensity of the step rates was higher in the machine control pace compared to the self-preferred pace, even though you have asked it to climb their maximum pace. And we see the difference here. When they have chosen their own pace, it was 90 to 103 steps per minute, compared to 109 to 122 steps per minute on the stair machine. So what we have found from the field study, if we check your maximal or little submaximal pace, you can only sustain 2 to 6 minutes, then no more. You will be fatigued and exhausted. At the same time, you can climb maximum 86 to 95 meters. Number 3, what we have found from the field study, if you want to climb for a long time, you should climb at 9 to 95 steps per minute. That can be lasted maximum also 9 to 15 minutes based on your fitness. So that is what you have seen is around 75% of your capacity level. Number 4, so if you climb until exhaustion, so we need oxygen uptake capacity level around 40 milliliter kg per minute. And when the heart rate will be peaking around 185 beats per minute. So what we have seen from the ascending step rate, the ascending capacity results are related to the step rates. According to 60, 75, 90, 100% level, we saw a nice correlationship. So we can see that physical evacuation model works fine and can be useful to estimate the ascending speed and distance and duration as well. And the model we have developed from the EMG data, this MACE and MARC, can be interpreted muscle fatigue very well. And so we can say from this study, the combination of cardiorespiratory capacity exerted by leg fatigue constrained the stair ascending capacities, while the VO2 max doesn't reach to your VO2 highest during a stair ascent. So if you have any maximum capacity, you don't reach to that level. So that is VO2 highest. So you cannot. So muscle fatigue will constrain your performance earlier than you're expecting. And finally, the altered gait biomechanics due to exhaustion indicated potential risk for parter gait when walking up a 10-degree inclined surface, and that can make any sleep accidents and can obstacle the flow of evacuation. So what I'm thinking for future. So I'm thinking we haven't done the until exhaustion for all the way. So I think it's better to do some more tests from 50% level until exhaustion. But we have done 100% level until exhaustion, but not 50, 60, 70, 80% level. So we need to do a different capacity level. At the same time, a different body height, body BMI, and different age group maybe. At the same time, we need to do the more frequent blood lactate measurements to compare the fatigue level. And we can use this, if you have EMG data, we can use the EMG data to interpret and compare the fatigue as well from the blood lactate. And I am thinking too more about kinematics in future as well. So how we adapt when we are fatigued. In the beginning, we see quite straight. At the end, we see some kind of struggling and adapting adapted strategies to when they're fatigued. So it would be good to elucidate the kinematics when someone is fatigued, how we adapt to the situation. Yeah, I'm thinking an app. We call it MACE app. So if we have an app and it is connected to the wearable EMG, and if we are working at the same time, and if we get the signals, okay, we are fatigued, so it can prevent any fatigue-related injuries in our workplace to get the continuous biofeedback from the EMG data. And finally, if you think about more walking speed, we only focused on one step. But if we want to know the walking speed, we need another extra force plate, which can allow to measure the stride length. To understand when if walking speed has been reduced due to fatigue, so it would be better to include a stride length within the kinematics and kinetics. Yeah, this is almost end. I would like to say this is not a one-man show. I would like to thank to my multidisciplinary team, including my. So here is one of head of project leader is present today, and my tireless supervisors, my colleagues, friends, I acknowledge your support all the way to be here, and also the funders, Brandfors Traffic Market, and later on Lund University, and the partners, brand, and also to the dedicated volunteers. Without them, it was not possible. And finally, my family. It was not possible without you all guys. Thanks a lot.
Thank you, Amitava.
You're welcome.
And please have a seat. Denise, are you ready?
Yep.
So I guess you have a presentation.
Yeah, can I share my screen?
You can share your screen, yes.
It's not that one. Okay, can you see that?
Yes.
Okay, thank you. Thank you for your welcome this morning and for the invitation to be the opponent today. I'm delighted to do that, and it's lovely to meet you, Amitava, and looking forward to our discussion later on this morning. So, as was said previously, I come from the School of Public Health, Physiotherapy and Sports Science in University College Dublin. So in this school, we have lots of, fit and active people. So it's considered quite a sin if you choose to take a lift, take the elevator instead of the stairs. So oftentimes, if I'm running to a meeting, I'm, looking over my shoulder, hoping no one's going to see me to take the lift, instead of walking up the stairs. But I think we can all identify with this research topic here, because we all know what we feel when we're walking up the stairs, right? So, you start off feeling pretty good. By the second flight or third flight, you're starting to feel a little bit out of breath. Your muscles in your legs are burning a little bit, and you might start to slow down once you get to the top, and you kind of say to yourself, God, I didn't realize I was that unfit, and so these are all very normal physiological responses to stair climbing, and that's really essentially what Amitava has focused on in his research. So from my perspective, I got involved in the area of evacuation or crowd movement about 5 years ago, actually with the Fire Safety Engineering Department in Lund, and colleagues in Ulster University and in Autodesk as well. Pete Thompson, I think he's online here. And so we came together. We were also funded by Brandfors, same funder I saw that logo just now. And we came together to think about how to model crowd movement in a better way than is currently there. So currently, the crowd movement is based on density. Okay, so the flow rate of crowd is based on the crowd density, and this data was gathered back in the 1950s or 60s, and it doesn't really take into account the changes that we're seeing now in our population. So it was data gathered on a healthy working population coming in and out of transport stations, for example, and other data as well. So it doesn't really take account of the older demographic that we're seeing now in the Western world, the larger body sizes we're seeing now with the increase in obesity. So our research was looking at getting more back to the individual characteristics and how the individual characteristics might be able to better predict crowd flow. So what we've been looking at is things like stride length, things like what distance does a person leave in front of them in order to have enough comfort to stop and enough personal space. And we've done some proof of concept studies that shows that, you know what, actually younger people and older people reacted a bit differently in that situation, in that older people seem to leave a little bit more of a gap when they're walking behind somebody. So that's just to kind of give you a sense of where we're coming from now, and again focusing really on the individual characteristics. So this is why, you know, I'm happy to see this research coming through, because, you know, it is very much focused on the idea of the person, the individual's physical capacity. So the VO2 max. VO2 max isn't something that we've looked at in our models yet, because we're focusing on certain things, but I think, you know, what this research has shown is that it certainly is a very important part of modeling evacuation, particularly over any long period of time. So for me, I suppose when I was trying to think about, as I read through the thesis, I saw it in sort of three different ways. I can see that it was motivated by what I call the applied problem. So, okay, how do we actually design these evacuation routes in terms of the physical load that somebody has to undertake in order to actually reach an evacuation point? Okay, so that's kind of the applied question, you know, how can we better design these things? The second thing that's tackled in this thesis is what I would say the methodological problem. And so when you're in a laboratory, for those people who maybe, you know, aren't scientists who are looking on at YouTube here, it's very easy to control a lot of things in a laboratory. When you go to the real world, it's a lot different. It's very challenging. And so when we do our studies in the laboratory, oftentimes they don't necessarily translate that well to the real world. So this is a problem that was touched on in this thesis. And then we have the biological problem, which is, well, how does fatigue develop in stair climbing at different intensities, and how does that affect performance? So I suppose, just for the sake, again, of people who maybe are not that expert in this area who are listening in today, you're going to hear about two important concepts really in the course of the morning. One is the VO2 max. And what that means is basically the amount of oxygen that is being used by the body as somebody is moving or exercising. Okay, so when we breathe in oxygen, okay, it gets pumped out through our heart, and it gets pumped through the blood system down into the exercising muscles. And so the more your muscles are contracting, the more oxygen is required to make energy for those muscles, right? So what Amitava has really focused on here is, okay, how much of that capacity is used. So the VO2 max is a very much accepted measure of physical fitness. Okay, and you can see here on the left how it's measured. You have to have this gas mask on, and it measures the air going in and out. So that's the type of setup that Amitava has used in his work. And the second thing is electromyography. Okay, so we'll hear it referred to as EMG, and what that is just looking at specific muscles and measuring the activity at those muscles. And you can see here on the slide on the left, we have these small little electrodes, and they're placed at very specific points on muscles. And you can see from the diagram in the center here that oftentimes the electrodes can actually be quite close to each other. And so it's quite a tricky technique to get right, and I'm sure Amitava will share his experiences of the journey to actually getting that right. And then on the right hand side, we have what comes out when you measure this is these bursts of activity. Okay, this is basically like a voltage, these bursts of activity that correspond to when the muscle is contracting. So those are the two main things that were measured in this study, and they were measured in different contexts and under different workloads. So Amitava has already gone through his research questions. I took the liberty to sort of paraphrase it a little bit. And so what VO2, so what oxygen carrying capacities correspond to what step rate, okay, both inside and outside of the laboratory? So that was the first question. What are the EMG characteristics? So what are the muscle activity characteristics at these different intensities? How can step rates be estimated based on individual physiological capacity? How can EMG characteristics be interpreted in terms of force production and fatigue? Okay, because remember, when you're looking at the muscle, you're looking at the muscle underneath the electrodes, right? So how do you interpret that in terms of overall fatigue? I mean, it's not that straightforward. And then how is walking performance affected by an exhaustive stair ascent? So I think I'd like to commend Amitava really for the amount of work that was done in the thesis. There's a lot of hard work in terms of the experimentation. There were a lot of subjects recruited to the study. So in each different context. So we talked about actually I'll just move on here. So we talked about the field studies and the laboratory studies. So there was 3 different field studies, and they were 3 different study cohorts. And then with the laboratory studies, there was two different studies, and they were also 2 different study cohorts. So there was a lot of recruitment and testing behind this thesis. Critically, I suppose the field studies were a self-selected pace. In other words, there was no, people were, I mean, we might talk about this a little bit later in terms of the instructions that were given, but they were told to basically choose their own pace. Whereas in a laboratory, you have a machine and you can decide exactly what steps per minute is being undertaken. So Amitava has already gone through a little bit of the findings there. I suppose for me, what this thesis has done is it has described the decrements in performance over time. It's characterized these changes in VO2, and it's characterized the changes in EMG. So it's put numbers on them. In these particular contexts, and that can be useful. So we know that the highest rate of oxygen uptake was around 40 for the self-preferred, and between 45 or 44, 45 for the very high intensity lab experiments. So we have a step rate range that came out of both the self-preferred and the laboratory experiments as well at the different intensities. And the EMG characteristics we can see were different between the self-paced and the controlled ascending speeds. We'll go into, I suppose, the findings in more detail during our discussion. So I suppose the practical implications of so how can this information be used? Well, this information can contribute to the knowledge base that is required to design ascending, durations. How long do we expect people to ascend for? What are the vertical heights? What would the step lengths be? And these kinds of questions. So we can derive some sense of design guides using the data in this thesis. In terms of the contribution to the overall field, as I would see it, I think this thesis provides a solid foundation for future research on the topic. So I think this is quite an exploratory research undertaking, It's given a flavor of how you might design experiments going forward in the future. So it's looked at the applied, the field test, and the lab test, and there are certain learnings from that that can be applied, by other researchers going forward, looking at this. As I said at the start, it highlights the importance of the VO2 capacity to build models in predicting behaviors in evacuation. It has provided some quantitative data on what intensity is sustainable for this particular cohort. And it has provided useful EMG profiles. So there's different muscles were examined during these processes. And now that we know how these muscles behave in these particular contexts, we can maybe generate some hypotheses in terms of how ascending performance might look for people who are impaired in the neuromuscular system, such as stroke survivors or people with arthritis. So that's all for me for the moment, and looking forward for a deep dive into the thesis later.
Okay, Denise, thank you so much. And thank you both for interesting and comprehensive presentations. And now we have a 5 minutes break. So you might want to stretch your legs. Just keep in mind to keep distance. And we will be back with you in 5 minutes. So, should we start again? Now it's time for the most interesting and exciting part of the Defense Act. Let's see if we have Denise with us as well. Yes.
Yep.
So, Amitav and Denise, are you ready?
Yes, I am. I should be
Yep.
always ready.
Yeah. So, please start your discussion. I will leave the floor to you both.
Okay.
Hi, Denise. We haven't met before.
Yeah, nice to meet you.
Nice to meet you too. Is everything fine with you?
Yeah, everything is
Okay.
fine. I'm here in this spare room turned office now for the last 2 months.
I see. Okay, great.
Is it possible for me just to share my screen briefly? I think it is, yeah. Okay. I just have, I might just dip in and out of a couple of slides here as we're going, but I suppose just to give a structure, Amitava, of how I'm going to go about this. Just, I suppose, 4 main questions really, which is why. Okay, so the why, the rationale for the research, the why around the different aspects of your study design. Okay, so I'll let you take us through that. Then we'll move on to the what. Okay, so what did you do and what did you find? Okay, and then the so what, which is, okay, how can we interpret that and why is that important or significant? And then finally, the what now question. Okay,
Yep.
so I have a tendency to speak fast, Amitava, so if you need me to repeat myself, absolutely go ahead and say so, or if you want me to ask something in a different way or whatever, just let me know, no problem.
I'll try to grab you. Take your time. Yeah.
Yeah, so first of all, I want to say that your thesis looked very nice.
Thank you.
Congratulations on that. It was nicely put together, and it was nice. It was a nice document to look through. And thank you for sending it twice.
By the way, did you receive the first one?
Yeah, the first one arrived 2 days ago.
Okay, great. Nice.
Yeah,
nice
yeah,
to hear.
yeah. So I suppose, in your own words, I would like to hear why you felt, why you wanted to take on this particular research study in the first place. You know, why did you want to do it in this way? What is important about this?
Well, I was interested. So you might have already heard that I have a background. I'm a physiotherapist, and also I have done the sports medicine here in Lund University. So I had a great interest on doing this sports science methodology to learn more about that. Then when I had this interest, then we suddenly got a project from, got contacted by the Fire Division Engineering. So you might have might have met Carl Friedel, who was the project leader when this project started in 2014. Then someone, Carl also my another supervisor, second supervisor, who also got involved. Then we were invited. Then he thought I can be doing this muscle electromyography measurements when we do these things at the same time, oxygen uptake. So that's the first I got involved. In the beginning, I didn't have any clue that I'm going to do this and this is going to be my PhD. I'm confessing that. So then now it's become my child. So that's the entrance, and then I thought how I can utilize this opportunity and maximize this opportunity to learn these methods in different way. So I have learned this. So from based on interest, learning oxygen uptake, EMG, ground direction forces, and force plate data. So and also finally I wanted to learn kinematics. Also from the interest of analysis gate, and also I was a sports physiotherapist in Bangladesh Cricket Board. So I knew that we need to analyze bowling biomechanics, batting biomechanics as well. So from that point of view, I also wanted to learn the kinematics and kinetics. So I tried to learn this, and from that interest, I have managed and I've come this far. So that's why.
So you were basically recruited onto a subject that was onto a project that was already designed, and that's how you started into this project, yeah.
This field part. So when it is not recruited, so I have got involved then. Then we have been involved to how to recruit, to announcement and planning how we can collect data, what should be used. But I have just said how I have been involved. Then during the planning process, announcement and recruitment, and then I have been involved as well after that.
Okay, perfect.
Yeah.
So can you tell me, Amitava, what was the rationale for choosing the 3 different field studies?
Yeah, so this is the physiological part that I have been involved, but in the beginning they had a plan to see the human evacuation behavior, how they move, and how. So we have done. So this part only focused individual part, but we had also the group behavior. But that time we only used one subject among them to measure the oxygen uptake. So when they had this behavior, and so we thought we need to look at the physiological part as well. So that part I and Caleb was responsible mainly to collect data for this.
And why? What was the significance of for example choosing the 2 different buildings? What was the purpose of that?
So we had this very short building very close by here. So in Lund, we didn't have any long buildings compared to this one, the 13th floor. Then we wanted to see it is very short duration. So you have seen this. The duration was about 3 minutes, 2.7 minutes. And then we wanted to see if it's long. So this is only 48 meter. But we have been here that there's a long stair flight in the subway around 100 meter, for example, in Ukraine as well. So if it is needed to climb long flights of stairs, so then we have decided to go longer, higher building. For example, the second in the fast paced second building that was 31 floor in Stockholm, that is Kista Science Tower. And if something happens in middle or in the lower part, so there is a restriction to go downstairs. So we need to climb upstairs. So that is also another thought. If some rescuing team are waiting in the top of the roof, so how fast we can and how can be human behavior at the same time measuring physiological capacities.
And yeah, okay. And so I suppose I'm still trying to understand how the 2 buildings were differentiated. I understand what you're saying about the stationary escalator is a kind of a long sustained ascent and quite a steep ascent.
Yep.
What were the differentiating factors between the 2, the 31 flight building and the 13 flight building?
There were different stair flights configuration. This 13th floor has 2 flights in between floors, and then 31 floor has 3 flights in between floors, and the stair width, height were different between these 2 floors.
And so did you expect performance to be different in those contexts when ascending performance?
Yeah, if you have more different stair width or step width or height, and more 2 short flights or long flights, and there are 2 resting planes in between the floors, how this can be different. That was another reason to look at different different configuration of stairways.
Okay. Okay, and so when you had that, you carried out that experiment, and I I'm sure that wasn't easy. And as I said, I do take my hat off to doing these experiments in the applied field. You know, they're when you get around to doing them, they're a lot more difficult than they maybe first seem. And so what was it then that pushed you towards the laboratory setting, or what did you want to find out by going into the laboratory and carrying out those experiments that you didn't already know from the field settings?
Yeah, so field study we have allowed to do the self-preferred phase, even if we cannot create any like a serious situation. We cannot put fire, and then it is difficult to get also ethical permissions for to get recruiting subjects as well. So so in the field we didn't know if they have taken the maximum speed or not. We just subject, and the people knew that this is not the real evacuation scenario. This is just a trial. So the lab test allowed to know the individual capacity level, what capacity level, in which capacity level, how far we can climb, how long the duration, and so on. So and also the stair machine we got, we knew that we cannot control the step rate, but it is allowed to simulate the escalator if it is even stopped. So some kind of escalator simulation on the stair machine. That was the idea to get the stair machine and do the test in the lab. At the same time, we are thinking if we can develop this model to calculate the step rates, and if we know human subjects maximum capacity level from the database or individual level, also we can estimate the step rate and ascending duration and height as well.
Okay, so the idea of testing the different exercise intensities was so that you could then predict step rate ranges. Is that right?
Yeah, and ascending duration as well based on the capacity. So we know that if someone is running and can speak, it should be around 50% level. So if it is 50% level and someone can talk, so we know that he has climbed or in that capacity. So in that capacity, how far a person can manage, and how is the oxygen uptake capacity level reaches, and heart rate level as well. So that was the idea, to know how far it can be. So we developed this model to calculate the step rate based on a 50%. But we finally have discovered this. The estimation has reached based on the subjects we had about 63%, 62%. So finally, our calculation validated on last 6 subjects from the second phase of the lab. So it is 60%, but we thought first in the 50%.
Okay, so by carrying out this study, you at the end you wanted to be able to say, okay, on average, you know, the average person when they climb at this percent of VO2 max, they do so for this length of time.
Yeah, exactly. So if we know, it's not common that everyone knows their maximum aerobic capacity. So if someone knows, and also there's estimation, like if someone climbs at 50% level, and if someone gives 2/3 of their capacity, 75%, so we would be able to know that this height can be climbed, and it will help to the definitely fire engineers, architects, planners to think about, like you said in your presentation, that they can use this knowledge to design the staircase and the flights, also exit plans as well. How many exits should be planned and executed in future? For example, deeper subways as well.
Okay, and can you tell me then, Amitava, like about what was already known about this in terms of ascending and climbing performances? What are more to the point, maybe what was unknown in the existing literature at the time when you undertook this work?
You mean which point of view? What is known? Can I
Like
ask you?
just the general area, you know, the state of the art, the other research that's been done in this area. You know, what was known about ascending performance and climbing duration and that kind of thing already before you came along and did your study?
So what I have mainly focused on the physiological part and then capacity required in this. I haven't found so much during the literature review. I haven't found so much on this physiological capacity level during ascending stairs. There are few I have seen. It was not exactly that how we have done. But I have seen some laboratory studies. They have also found they have used a similar type of stair machine, but not exactly the same. So there are not so many. Only 2-3 studies what I have found during my literature review. So it's about around like that. 43 milliliter kg per minute. One lab study I have seen. So they have also climbed for 5 minutes in that stair machine they have used, and also one couple of field studies they have done also, but on 20 floors. Until 20 floors, they have found also around 37 or 35 milliliter kg per minute. Halsey et al. It's in one of my reference as well. So it's not so many what I have found so far in this area. So that's why I found this is quite unique. I'm thinking, but the other different professionals in this field will be able to identify if this is more, let's say, this is more usable for their in their field to apply this knowledge when they're planning the evacuation. Yeah, I'm talking about this Halsey et al. If you look at 101, page 101, they have used this energy expenditure of stair climbing 1 step and 2 steps at a time. Halsey LG, 101 page.
It strikes me that because I know you're focusing on sort of civilians, right? You're talking, you know, I think from what I'm understanding, like this whole research is focusing on sort of the average person, you know, walking through the built environment. It strikes me, of course, that people who generally run upstairs in evacuation would be firefighters, right? Because they have to run up the stairs usually to reach people. And so, do you know anything about what level of intensity that firefighters are ascending stairs?
Yeah, when I have studied the firefighters, you of course know that they have a higher physical fitness compared to the general population. And what I have gone through that their fitness level is also around 43, 45. That is recommended to have to be as a firefighter. So when I did this literature survey, so I have seen that they have this, and it's about 80% capacity, I think, they have done. For
that they're working 80% of their capacity.
Yeah.
Okay. Okay, so I suppose I think you've covered the why there, I think. So I'd like to, I suppose, look at the what now a little bit. I'm just going to share again my screen. And I liked this table in your I liked this table in your thesis because it was quite nice to see, you know, all of your participants and what data you were able to get from all of them, right? So so we can see that, okay, you recruited this many subjects, and then, you know, some of them you got the VO2 max data on, and some of them you got the EMG data on. I'm curious, I suppose, maybe you could talk about you know, if there's other PhD students out there thinking of using EMG measurement and VO2 max measurement in the field, could you explain to them what challenges that they might encounter from your own experience?
Yeah, this is a totally very nice question, I think. If somebody is interested, that I think is using electromyography based on the method I have used, and that is more reliable. But if there are possibility to use, there in the market now is available also wearable EMG using EMG pants and the EMG shirts. If it is, I'm thinking in future to develop more wearable EMG. It's under validation. But definitely it is very challenging to find subjects as well, and also preparation, and also needs some kind of experience beforehand. That so it's I also have this experience by gradually doing. I have studied in 4 or 5 studies already, so that's why it's not very that it's not impossible to do. It's time consuming as well, and also in the field we have found problems for subject preparation. To to make subjects ready, need to change clothes and put the electrodes, and sometimes it is required to shape if someone is a bony hairy skin, and also prepare the skin to put the electrodes, cleaning, and sometimes need to scrap the skin a little bit to take away the debris, dead skins as well. So it's not impossible, but it's manageable to get some kind of idea what muscle activities are there in different intensities. If someone wants to know that what is happening to the muscles when someone is climbing, and we got some idea which intensity they have got, but also EMG has different limitations as well. So
can you talk about them, the limitations of EMG?
Yes, also so if you the same subject, if you do the for example maximum voluntary contraction, it can be different in the same day, and in the same day and the same time. So it's also it varies a lot. So I have also had difficulty to normalize the EMG data as well. So when I tried to normalize the real data with their with their maximum velocity contraction data, I found sometimes I expected maximum voluntary contraction would be highest for a specific muscle, but unfortunately, maybe my method was wrong. Maybe the position was not good. Some subject we didn't manage to encourage properly. It may happen, but so far my knowledge, we have tried our knowledge based to encourage the subject to do the maximum voluntary contraction for that specific muscle, for example, thigh muscle, and then also put in a position where they can exert their maximum force for the knee extension, for example. So then we found in the real, when we try to normalize the EMG data, and we found this maximum voluntary contraction is very low. So these sort of things, sometimes then we had to do the maximum amplitude from the real test. Then we have used that one to normalize the normalize the different time normalized periods. So these sort of challenges we have discovered during the field study, because we didn't have enough proper setting to do the VO2 max maximum voluntary MVC test in the field.
So what did you do? Did you do a maximum voluntary contraction in the field?
In the field, of course, we had to do.
Yeah.
We tried to arrange a bed, our sitting position for the thigh muscles, and the lying position for the calf muscle, and sitting position for the anterior leg muscle as well. So but it was not only standard position, I would say, because we had to compensate how the facilities we can arrange in the field. So during the field studies, EMG measurement is quite challenging, I would say.
I remember about 10 years ago, I was a postdoc and I was working with a student who was looking at EMG and stepping, and I was looking at the biomechanics component, and we were all excited because we had this new wireless EMG, and it turned out that the data that we collected really wasn't that good, because we weren't expert enough at that time with the new equipment, and the data was actually unusable for the most part. I note in your thesis, you say that you said EMG signals containing excess noise were excluded from the analysis. I'm just wondering how that was judged and how many trials were excluded, and were they excluded at random, or was it, you know, was there something systematic about the exclusion, or can you talk a little bit about that process?
This one way we normalize the data by using the MBC value, and then also we had this process called, we use 50 notch 50 hertz to standardize the data, and also we had 10 to 500 hertz for processing the EMG data as well. That we have done in the field study, we have done in the using the MegaWin software, but in the field in the lab study, in the last phase, we have used the MATLAB to using the same value to process the EMG raw EMG data.
And so when did you exclude, when you say that you said some EMG data was excluded from the analysis, like when would you exclude?
Yeah, that is interesting. Sometimes EMG values were amplitude we have found 2000 hertz or 1000 hertz, 1000 not 1000 microvolts. So then it is more than 1000 microvolts, something that is quite unreasonable. So in those cases, and we found maybe sometimes when you saw the raw EMG data is quite frequency is quite wide and totally like block and different things, then we don't see any reasonable in those. When I have gone through individual data, all those were not considered for processing further. Then we had to exclude those values.
And how often did that happen?
It's not often. I have in the papers I have mentioned how many subjects. It's so far I can remember from the, if I don't look the paper right now, from the field we had maybe 3-4 subjects, and in the lab it was not so many, maybe 1-2 subjects or maximum 3 subjects in each phase. It was better gradually with my experience, and also the electrode placement and the distance, and also in the lab we had some control and we didn't need to make hurry as well. We had enough time to prepare. We had a proper settings to do the MBC test, and we could have planned properly, but in the field it was like subjects were coming very at a time 2-3, so we had to find one of them to pick, and then who was agreed to measure the electrodes and who had a convenient clothing to change in that field settings. So those sort of things were difficult during the field studies, and also it was also affected EMG electrode placement preparation as well. That's why you also got some erroneous data in the field. So that's why you lose some data as well.
Okay, so looking at that table on that I'm showing on my screen, I don't know if you can see it right now. So the fact that, let's say, you know, in the study on the 13 flights of stairs, at the 31 flights of stairs, you started out with 47 subjects and ended up you could only get EMG from 12 of those subjects. So would that would have been a combination of people agreeing to do it, and also maybe some subjects that you would have excluded subsequently based on the quality of their data. Is that right?
Yeah, so you have seen these 12 subjects have been measured in the 13th floor building. So those who have agreed, but it's not always that all subjects that this exactly 12 subjects have been included, but some values, some trials were not during some part of period of the ascending were excluded when we have seen this erroneous data in
Yeah.
specific in that specific subject.
Mhm.
But we have found 12 in the 13th floor building, 9 in the 31 floor building during field study, because they were coming in a cluster, so 2, 3. So because they could come exactly like end of the office hour. So then they've come together. Then one was agreed to do that. So that we had to find one of them. So we didn't have so many days to arrange the field test in the buildings and also in the skeletor as well. So we had to do very short time, and then the small number of subjects we managed to measure EMG data for in the field.
Yeah. Yeah, that's fair enough. Okay, so that's about the data collection piece, I guess. This model that you use is quite interesting.
Yeah.
You show. Can you see my screen, Amitava?
Yeah, I can.
Yeah. So as I said before, like, you know, with EMG, if you had the best data ever, okay, the most perfect data, okay, you're still just getting data from a very small part of the muscle. And so, you know, the question is how do we, you know, what can we infer from that in terms of the fatigue of the whole muscle, or indeed beyond that. And I suppose this is what this model attempts to do, right? It attempts to understand the behavior of the muscle. And by the way, so the decrease in frequency was your metric for quantifying fatigue, right?
Exactly. Mainly, if the frequency goes to lower end, then we could quite confirm that there is a fatigue onset of fatigue.
What causes that, Amitava? What physiological mechanism is causing that reduction in the median frequency?
So during the, for example, if I give an example of the maximum voluntary contraction, so recruitment of more motor units are decreasing with the time. So then we don't see more frequencies getting lower end with the time. So that's recruitment of motor action unit action potential is decreased. The recruitment of number of motor units are decreased with the time. That's the frequency we can see from the frequency metrics.
Okay. So when I was looking at this, you know, it struck me as like, this is quite neat. You know, this is quite tidy. And I just wonder, are things really that tidy in real life, you know? And so for me, I feel like to really validate the assumptions in this particular model, you'd be talking about another PhD, really. You know, if you were to validate the assumptions empirically here. Now I know a lot of research has been done, and certain assumptions like are more proven than others, I would say. Would you agree with that?
Honestly, I haven't seen that this has been, if I'm interpreted your question correctly. So you said, has it been validated in some places or not? Or
Yeah, okay, yeah. You
No,
can talk about that.
I have we have got this idea from if you have seen this paper, Sifrex, who has done this 2009. He has first proposed this kind of idea, and then
Well, he actually, sorry to cut across you. I did go to that paper. I read that paper, and that paper referenced another paper, and I read that paper. And I pulled some data out of that paper that we'll talk about in a second. But go ahead, because I'd really love to hear you to critique this model, and tell me about the strengths of it and the potential weaknesses of it.
if you look at this, it seems quite reasonable that when amplitude increase and frequency decrease, that's fatigue. And also what we can see from our data, from our laboratory study data. So we can confirm from the that they have reached fatigue, that we can confirm from the lactate level, and also we have seen this, they have reached when they have when they have set their perceived exertion on the Borg scale as well. And we have seen also observation that they were exhausted totally, they couldn't climb at all. And then we have also seen this individual amplitude and frequency data. So in this, the model, in that assumption, then when amplitude increase and frequency decrease, I think it's quite reasonable. And then we have seen, if we compare this assumption to the field study, that's also reflected in our this one in our model is a maze, mass-select interpretation. When we put the mark, the changes between 10 to 20, 20 to 30, until the 100%, until they reach the top of the building. At the same time, when they reach their exhaustion level. So I think it's reasonable. That's why I thought if we make these two parameters as one parameter, then how it looks like, and then it seems quite reasonable, and it's I would say it's quite valid. And then we have also used in the field study, and then in the second phase of laboratory study that is also published in Ergonomics, and then first one is applied ergonomics. Now is the paper number 4 is now under review, and I have submitted second division, and we haven't gotten so much comment on that, honestly. So it seems it's accepted, or it's, yeah, so far it hasn't, according to the data and the comments we have got, it seems it's quite valid. And but definitely, as I said, I'm also, if I have any opportunity in future to do more tests in this stair ascending level, then we also can valid and also update, and also we may need to do this time normalization for whole duration, maybe in small segments, not only whatever the duration is. We have divided only 10 different time normalized period. It can be very smaller, can be 20, can be 15, based on the duration. That we need to think about. I haven't think about that so much, but so far, so it looks like it's quite reasonable based on this assumption, and if we make one point that is mark in the maze.
Just a question that occurred to me there as you were talking. You talked about this time normalization and breaking it up into 10%. Did you consider looking at the step as a unit of EMG analysis?
Yep.
As opposed to the time, and why did you choose one or the other?
Yeah, that would be best. But so you mean the walking step, or?
Yeah, like just because it's so cyclical, right? Like that it would make sense to look at the EMG profile per step.
Probably you have seen because in the last part of the last phase we have reported the EMG data for the stance phase duration. So I don't see in my naked eyes, I don't see any differences. If you look at the last paper, page 16, So we have this. I can also show in the. If I go back to.
Which paper, sorry, Amitava, is it?
Last paper.
Paper 5.
Yeah, paper 5, page 16.
Yeah.
So this is the. Can I share that one? It doesn't work. I need to maybe click this one. I should go back again. Huh? PowerPoint. Okay, so if I go back. So many. I'm there. Thank you.
Should I stop sharing? Is that
Yeah,
the problem?
it's if you can see this one. So here's the whole stance phase duration, pre-fatigue. Can you see the?
Yeah.
Okay. So this is the whole stance phase duration before fatigue and then post-fatigue. So the first row is for the first row is for amplitudes, and the second row is for median frequency. So this is the whole. I don't see anything in here, and we didn't. This phase is very short in order to interpret EMG data according to these results. So that's why I. But if you only want to know the number of the value of the amplitude, that is possible to know, but we didn't find any significant result based on the amplitudes, but only if you look at the frequency, similarly as we have seen during stair climbing as well, this vastus lateralis, thigh, and tibialis anterior, these two were significantly lower. So mainly maybe that is during a stair ascending on the stair machine, because machine step height and width were very small. Height maybe is enough, but the width was very small. That's why this TA muscle, tibialis anterior, was very fatigued. So it was affected. They had to hold always the foot on the, because step rate was very high as well. So that's why we found these two muscle fatigue that we can see from this step. If you are thinking about one step stance phase duration.
Okay. So I just want to get back to this, because I really want to understand this as well as I can. This model here. So this data is a plot that I took from, a plot that I took from Lutman, which is a paper that was cited by Sifrek or?
Yeah, Sifrek, exactly.
2009. So this was the kind of original paper that came up with this model in the first place, and and so it showed, this paper showed this data to support the fact that with increasing median frequency, the force also increases. So that's one of your corners in your model, right?
Yep.
One of your corners. It's when the frequency increases, the force also increases. So that's one of your 4 assumptions, I guess.
That is top right. Yeah.
Yeah. So what he has shown here, he's shown a bunch of other studies that have looked at this and that have shown that as as the median frequency increases, so you know, so does force, but it only goes up to 60%.
Okay.
See that? To see that it kind of reduces a little bit after that. So I wonder if you were to look at this data now, would it be the case that using the model that you've proposed might be more suitable for certain intensities versus other intensities?
That is quite difficult to answer for me because exactly, do you know what type of activities they have done there?
No, this I don't, and it wasn't stated in the paper, and you know, so it wasn't clear, and it's actually even a mixture of muscles as well, a mixture of lower limb muscles, so it's not even all the same muscle. So they're basing the assumption on different activities, different muscles, but that there's a general trend, and this is the general trend that they show. And that's what led them then to make that assumption in the model. So I think your answer is quite right. I think it is difficult to answer that question because I think the data maybe hasn't been well, I don't know, maybe the authors did look, it certainly wasn't reported in their paper in terms of what exact activity it looks at and what muscle it refers to. So you're seeing a similar issue to what I saw, right?
Yeah, exactly. In that case, I only can look at this paper and try to identify if I find it. I try to identify what activities and intensity, and then. But right now, I can't say so much. If this data will be can be used to model the way I thought. I'm not so sure.
Yeah.
Yeah, but it's a good. I think you have found this. I think it's quite interesting. So it would be. So I see many possibilities to validate this model using different activities, not only stair ascending. It can be used different activities. So it's the way I see the model is to use the EMG as a easy way. EMG should be because when I have done this, I found it's very complicated. A lot of processing, a lot of things. So I need a very simple solution. We have developed these codes in MATLAB. Probably we can use this and in an app. So if EMG is connected to that app, so probably it will be converted and gradually it will be just giving a point. So you are fatigued or not. So that's how I see to use EMG in future. If I am.
Yeah, I think that's a good point because you know if that were actually to be possible that you could develop you know a reliable app to collect that data, you know, in lots of different contexts and activities, you know, there could be nice data analytic approaches that could then maybe move towards validating this model. But I suppose I think it's really nice, as you say. It's nice. It's simple. It's easy to kind of you know visualize the two characteristics of EMG data. But for me, I suppose I would still see it as quite exploratory. As far as I understand it now. Would you agree with my understanding or?
Yeah, only thing now this model is validated in only one activity, that is stair ascending, and I haven't used this one for other activities. So it would be good to use this one if someone, if we have more students in future, or if you see in your country new students, maybe if they want to try this model in their field for other activities, then I would be able to say strongly that this is good. But from the data I have right now, from only one stair ascending data, only based on 3-4 studies, so that's what, in that point of view, I can say that. But still, like I said, in only this stair ascending study, we may need to divide the ascending duration in several divisions, not only 10% to not only 10% each for whole duration. It can be, and we have to find out how long the data. So if it is 3 minutes, how many segments can be divided? If it is 7 minutes, how many segments needs to be divided? So we have to think these sort of things that we haven't thought so much. Whatever 3 minutes we have divided in 10 divisions. We had 8 minutes data. We also divided in 10 divisions as well. So these sort of things needs to be thought in future.
Certainly, I agree with you there. So what we're looking at here, so just I want to make sure that I have this right, okay? So what we're seeing, so each dot represents a time period, right? A normalized time period, is that right?
Yes. For example, you see this one dot is either 10 to 20, 20 to 30, 30 to 40. So
and that dot is the average of all of the subjects.
Exactly. All of the subjects for amplitudes and then frequency, and then changes from 10 to 20 for amplitudes and changes for 10 to 20 for median frequency. These two changes value were divided by the average time duration for the whole duration. For example, 3.5 minutes. So 0.30 was used to divide that period, that value, and then combine these 2 points to make 1 point. That is mark.
Yeah, and I appreciate it wouldn't look very nice on these plots, but what are the sort of the error bars or the variation across each of those points?
Yes, that's a good point. You have noticed that. We haven't used any error bars in here. It's only the scale how it came naturally when we plotted this. That's another thing. We haven't used any error bars because we considered that EMG data has been processed using notch filter and then normalized with their maximum voluntary contraction. Then that's why we haven't done any error bars in here in this to plot this data.
So here these are the plots for the field studies, and these are the plots for the 90% and 100%.
Yep.
I suppose you could kind of say that these two plots look somewhat similar.
I would say that 90 and 100% is quite they're close. I can have a look, but I can
even though the duration was quite different, yeah.
Yes, because duration was different, but not that much, because one was 4.3 minutes, 90% level, and then 100% level average duration was 3.5 minutes. And one important thing is this model would be useful if we can make it for individual subject, because now it's an average data for all subjects in here. So if and fatigue is also individual, and individual has different capacity. So now we have combined different duration data and put in a one plot. That's another drawbacks in this, what I personally feel. But if we want to know individual fatigue level, that it should be done for individual level. Then I think this plot will be depicted very in a better way. Then we'll be able to interpret in a proper way than how it is at least in this point as an average data for from EMG point of view.
Okay, yeah, I think that's a good point that you're making. So can you tell me, just in short, kind of simple language? Okay, so I'm back at the field study plots here. What is going on here that's different from the 90 and 100% plots? Like what are we seeing that's different? Can you sort of interpret that a little bit?
Could you please point one muscle? Then it would be easy because you have 4 muscles here.
Yeah. How about we say the GM?
Yeah. A GM with field and lab.
Mm-hmm. But first of all, they're quite different across the field studies, right?
Yeah. So in the GM, you also I would also mention one couple of things here. In the beginning, we are not so sure which muscles should be. That's why we also choose also both calf muscle. Then we finally, at the end of the study, we finally come up that we should not measure the both calf muscle and also the. But if you look at the GM, we did.
Sorry, Amitava, why is that? Why did you make that decision? Just
because we thought to pushing off phase, we need to use both. We need to measure both calf muscle. Calf muscle is important when we during the swing phase and you carry your body weight. We need to use. Maybe calf muscle has a great role to carry your body weight and move forward. So and also only thought the thigh muscles as well, anti-gravity muscles. But gradually we then it was the both calf muscles were measured in the field, then in the and also 90% level, and finally I thought it's not needed to measure both calf muscles. Instead, we need to measure the one of the anterior leg muscle that we choose TA muscles. But if, as you said, if we compare the GM here and the GM with the 31 floor, because it was long, about 8 minutes, we can see this 100%. 80 to 90 and 100%, 90 to 100% dot points are belongs to, especially 90 to 100% are belong to muscle fatigue square. In the if you look at the 31 floor building on the GM muscle. At the same time, if you look at the 90% view to max step rate, that is GM muscle, we also see this even though period was short. This 90 to 100% point was in the fatigue muscle fatigue square. So we in the field it was longer duration, but in the lab it was also short duration. But both cases were fatigue. So in that way it worked well.
Yeah. Okay. Yeah, so I suppose for me as well, this idea of change in the median frequency, how much change is meaningful is a question that came to me, particularly in your study 2, because I think you mentioned. that there was in plot C there. I think you mentioned that there was a statistically significant change in the rectus femoris and the vastus lateralis over time. Is that correct?
Yeah. Yeah.
And yet it seems like a flat line there.
Interesting. This also we also discussed this. Even though flat lines and how the statistics, this is the statistics value what we have presented in this paper, and also frequency point of view, maybe these small changes also maybe the standard deviation was very high in that case, those cases maybe but we have also looked at what is called this plotting, using the plot to see the spread of the data. So then when we saw it's not spread well, so we have decided to do the Friedman's test to see the changes. So then this is the Friedman test value what we have done for this for this frequency and amplitude
So
data.
and so does the Friedman test capture the idea of repeated measures?
No, only to when the data was not well spread and what is called this? Forgot the term.
Normality.
Normality was not supported. Then we have just only do the non-parametric test instead of doing any parametric test.
And so you compared across 10 groups.
Yes, these 10 divisions of the whole durations.
And can you tell where the statistically significant difference occurred?
What do you mean, when or?
Like between which time point?
No, we have just checked overall. Is the difference from 10 to 100% duration, is that significant or not? That we haven't looked specifically which duration. We just check the p-value or value for the whole test.
Okay. Well, if we leave the statistics aside for a moment and just look at the data, like, how do we know? I mean, as I said, I know there's a kind of a little bit of a scale issue here because we're looking at four muscles in the same graph. But as I said, like, it looks kind of like a flat line, right? So, you know, is there anything in the literature that tells us like what is actually meaningful in terms of a change in?
Yeah, what I have found is this, as I say, as you have already discussed, this change or shift in the median frequency or mean frequency of a surface EMG power spectrum toward lower values, and that can be one way. Another way it can be the increase the power of the low frequency or the decrease of power of high frequency. So that's this part I haven't looked at, and also I haven't looked at the mean frequency. So only the median frequency that is commonly used. But I think this is also quite interesting, the point you have made. I think we so for this is another challenge, like you mentioned, for the EMG measurements as well. How you interpret and which parameter should be considered, and also activity is different. Individuals are different. Individual muscle characteristics are different, and genetics are different. So a lot of different other things we need to consider when you think about EMG muscle activity data. And also it is surface EMG as well. If we could have any wear EMG, that could have been could give better results. I don't know. We haven't used that, and we have just used surface EMG, and based on surface EMG, it's to get some kind of idea to understand how the muscle activity, and if there is any fatigue or not. If it is interpreting how we interpret, just say just saying a subject, seeing a subject if you are fatigued, to get some idea by having some physical observation or practical observation.
Yeah, I mean, so I suppose we spent a lot of time talking about the EMG data because I suppose it's quite complex. On the other hand, your the oxygen uptake analysis, your data, you know, seemed to align with what we know happens in you know, in VO2 kinetics and that kind of thing. So it maps pretty well to what's out there. Is that fair to say?
Which one you are focusing right now, field or lab?
Just in general, like in general, what you found was that you know, that there is a sort of a sharp increase in oxygen uptake, and then it goes into steady state afterwards. Yeah.
It's a normal physiological process. It doesn't oxygen uptake doesn't reach immediately after starting. It takes time, about 2 to 3 minutes, to reach the required. All the muscles needs to be active, needs to be worked, and all the oxygen needs to be consumed and by the body. So it takes about 2 to 3 minutes to reach a stable state. And also it also differs. It is self-preferred pace or control pace, and if it is a control pace, and which activity intensity level. So that's also come into we need to consider when whether it is stable or not, if it is very too high intensity, if it is a critical power or not. So those needs to be considered when we look at the oxygen uptake data.
And did you encounter any challenges when you were collecting the data, and if so, how did you solve those challenges?
Compared to EMG, I haven't found so much challenges measuring oxygen uptake, except a lot of subjects were many subjects were discomfort with having this mask on when they were doing this stair climbing, even in the field. It was very difficult for them to climb without holding the stair machine handrails, because the mask was blocking their view. They definitely need to hold the handrails on the stair machine. But also people didn't like to. Some of them have complained that it's some kind of feeling suffocating. It doesn't feel that they were taking enough oxygen. It's some kind of lack of oxygen even felt, even though it was based on their based on the workload. But they felt they were feeling lack of oxygen, or complained about that. It's yeah, those sort of small minor things. But otherwise, compared to EMG, from my experience, I haven't experienced so much challenges in when we measured VO2.
Yeah. Okay. Very good. So I'm going to move on to this. Can you see my screen? Yeah. This graph, which is in your last study, I really like this graph.
Yep.
And if you just look, I'm looking at the ground reaction force here up top there, yeah.
Mm-hmm.
And so, can you just like describe to me what we're seeing, just without necessarily using numbers, but just qualitatively, what are we seeing on those graphs, particularly in the Z component, before and after exhaustion?
Yeah. So we wanted to see, my hypothesis, or some kind of hypothesis, was like the forces will be different. At least I expected lower forces that we have found during hill strike, and also the Z forces point of view. During hill strike, I expected that they will not be able to produce same force as they could do before fatigue. So that is supported, that we have seen lower ground reaction force, normal force, that is vertical one. This blue one, that is lower. So we have normalized the forces with Newton per kg kilograms. So it's although the difference is very small, statistics show that it is significantly different, significantly lower during hill strike post fatigue. Yeah. And also during
yeah, so that actually, I mean, I wanted just to talk about the kind of the shape of the graph first, but as you mentioned it there, yeah, there was a reduction in ground reaction force pre and post. It was small though. It was a small reduction.
Yep.
And then you use those values to calculate the coefficient of friction. Sorry, my brain went a bit different. But I was really surprised to see like the change is really so small here. I mean, you're talking 0.001 of a difference, and that came out as being quite highly significant, actually.
This is quite interesting, and also this is what we have found, and then it is based on the statistics and based on the t-test, and then that's what it shows. This 2.69 and 0.70. So this sort of difference when the standard deviation was 0.804 in both cases. Maybe that is when the standard deviation was very equal. Then this 0.1 is like that is significant enough to when we compared these two values. So that we see this higher required coefficient friction was required was higher, to maintain the stability and balance after fatigue.
So coming back then to the graph, because I want to talk about this nice graph here. So what I'm seeing when I look at this, I'm seeing that pre-exhaustion, all of the people are your subjects are quite tightly bound, into one pattern there. And afterwards, then it's not so. There's a whole lot of different strategies, coming into play here, whether they're adaptive or maladaptive strategies, we can't really tell. We don't have that information, but so that's interesting in itself, right? So we can see, this is a really good example of just how things can, because in some cases the force went up for some people, and in some cases it went down, right? What's this little thing here? What's going on here?
Interesting. You pointed this out. Yeah, I can say some. Probably we would have needed some kind of because this is more quantitative data. We should have done some kind of qualitative analysis here as well. So when we have seen that, what we have seen after exhaustion, they were even faster. Some cases they tried to make balance, and some people were even stumbling on the way when they were walking. They were trying to find like a proper walking pattern, because we even tried to make them walking just immediately after they have finished climbing after on the stand machine, and then we had to spend maybe a couple of maybe around 20-30 seconds to puncture the fingertips to get the drop of blood, and also they have expressed their subjective expression on the perceived exertion on the Borg scale. So this sort of time we had to spend, but I don't think they have recovered in that time. But they were quite fatigued, and sometimes they stumble. Maybe these cases I have seen. I can remember because I can remember the faces those who have stumbled. So because they were also local students here around us, so also some of friends, so university students mainly. So so these sort of cases, and yeah, so maybe stumbles or someone is falling, or we didn't experience any serious fall because it was not that any case, but those sort of cases, maybe stumble or trying to make balance when they're walking, and then someone walking with long steps, those sort of cases what we've experienced.
How many subjects would you say exhibit this sort of transient early peak? How many? I mean, I can guess here by looking at the graph, but do you know?
Do you mean how many subjects?
Yeah, how many subjects actually demonstrated this early impact peak?
Not many. I think if you think if you think about the ground direction force, if you look at the level 8 to 10 Newton per kg, if you look at that peak, then maybe 5, 6, or if you look at this 14 in here.
Yeah.
So if it is 14, then sorry, here is not many, 1 or 1, but if you look at this one, then it's maybe 5, 6.
Yeah. I mean, I think that, I mean, what it looks like to me is this sort of impact, very early impact peak as they're hitting the ground.
Yeah.
And we see something similar in running, depending on whether like barefoot running versus shot running, for example. You see this little impact peak, and it's usually related to some sort of change in stiffness of the leg.
Okay.
So I'm just trying to kind of tease it out here, and I'm wondering, because you found that the I'm just going to go to the next table. So you found that the absolute angle of the ankle to the floor was lower after exhaustion. So in other words, the foot was closer to the floor after the exhaustion. Is that right?
Exactly.
Okay. And so therefore that would suggest not a very stiff ankle, right? Because it's a little bit more, just to use an unscientific word, maybe a bit more kind of floppy. Then in the knee, you have what looks to be like, even though it wasn't significant, it looks to be like it's a straighter knee.
Yes. Yeah.
It's a straighter knee at heel strike, at least. Yeah, it's a straighter knee at heel strike, which could suggest that maybe that there's something around the leg stiffness that's giving. It seems like it might be a strategy that some people adopted in their fatigue state. To adopt, to try to kind of get use a stiffer leg to walk. I mean, it's just a theory looking at the data. It's a possible explanation, but I think you should, because you don't really talk about this in your discussion, right? You don't really talk about this transient peak. I think it would be nice to tease out and look to see how many people actually have demonstrated that,
It's very nice to see that you have observed this one. We didn't, honestly, I didn't focus on that one so much in this paper because I only thought about the peak, because that is not the peak. Peak, I thought it is, because also this is maybe part of the period we have excluded to calculate the required coefficient of friction. So maybe not, but for when we calculate the ground reaction forces, we have taken the whole 0 to 50% period. What is the peak in that period? But,
yes.
But for RCUF, so we only focus on the peak. We didn't think about this pre-peak, at least in this study. But it's a good observation. I really appreciate that you pointed this out, and it would be good to observe. And we have this kinematics data. I can look at the if I have time to look more about the strategies, as you mentioned, what they have.
Yeah, and actually that's what I was going to ask you next, because you mentioned there that you said some people even got faster in the walk afterwards. But am I right in saying that you actually haven't reported the duration of the walk?
No, we haven't found that. We have found this post-fatigue duration was shorter, if you have seen that.
The stance time is shorter,
Yeah.
but I mean the walking speed, so the time taken to complete the walk altogether. I mean, were people moving faster or were they moving slower?
Yeah,
in general?
we had a limitation here to get these results, because we have just managed the synchronization, but when we started this trigger and I started the measurement, and sometime it's frozen. So we had to start the measurement just before they were striking on the frost plate. So we had to wait quite a while. I don't know, it was a new instrument or there was some kind of, we had some old cameras, like third generation Qualisys camera we have used, or second generation, I'm sorry, second generation we have used. There was a time lapse between the synchronization to activate all three instruments. So we couldn't record the whole walking.
Okay.
That was drawback. That was one of the biggest drawback what I see from this study. We only recorded just before striking the frost plate.
But even still, you have marker data, right? Like you've got a marker on the hip, for example. Right?
Yes. Yep.
So you could look at the change of displacement of that marker, which you've captured because you triggered at that time, right? So you can record how quickly that step was taken, right? or how many strides do you have? Like if you just think about the hip marker, for example, so you clicked your thing, it's synchronized, and how many steps did you record then after that?
So we total to reach to the first plate there were 5-6 steps, and after crossing the first plate there was 2-3 steps, not so many.
Okay.
So we just focused on the because what I was thinking, because I know this kinematics is very complicated, what I've also experienced, then I thought again similar way for the EMG. If I can say something based on this very small duration, if we record very small duration, that is the stance phase, and if we can say something about the altered biomechanics due to exhaustion, that was my focus. And that's why I didn't analyze anything within this period. But I wanted to cover the kinematics and the effects of fatigue on the gait biomechanics. So that's I just took the stance phase duration.
Yeah. Okay. I think it would really add to the paper to give some sense of the speed of movement, you know, and I think you can get that from your data, right?
Sure. That I now I got the more I got more interest now because you have pointed this out. That is very productive, I think. I would love to.
I think because I think it's hard to interpret the reduction in stance phase when you don't know how fast they were actually traveling, you know, that kind of way. So I think maybe something to look at. So I have a question.
Yes.
I suppose at the start of my presentation, I talked about the fact that I'm interested in, you know, age, you know, how more aged people move in comparison to younger people, and how that might influence evacuation dynamics, etc. So I noticed that some of your cohorts had quite a range of age, and I'm wondering, did you consider looking at that separately, older versus younger, or because it seems like quite particularly it's evident in the range, the step rate ranges in the first laboratory study compared to the second laboratory study, which only had healthy young people.
Exactly.
And so the step rates are so narrow there, whereas they're quite wide in the other ones. So it seems to me that variability might be due to age, but I don't know the age profile really of your cohort, only the age ranges as you've reported. So can you talk about that a little bit?
Yeah, sure. So in the field, we have also very wide range of people in terms of age. So we also have done the same in the field, second phase of the study, but first laboratory study. We also had similar. We wanted to cover different age groups. We had 25 in the second phase of the laboratory. So that's because we knew that we are going to run the test for 3 minutes in the first two levels, 60 and 75% level. So that is not long. I think it's manageable for all subjects. That is one thing. And also we don't allow subjects to climb more than 5 minutes to see the VO2 uptake pattern. So in that case, we considered all subjects, and then we were not so sure how it will be because this stair machine I also tried by myself, and then I found it quite difficult for to allow different older age group, for example, but it's manageable for younger population too, because even though it is hard or to maintain the step rates, and because it's for training and it's not very practical in that point of view that you run very fast when you're older. So but in the final phase of the study, we recruited all those who are very fit, and that's why we see very small range of step rates in the last phase compared to the second phase. But it would be very nice, and I've got one of my colleague from here. He was a security officer. He gave me a prototype, like how can be a new step machine, which is which is possible to control the step rate by the subject, and also more wide in terms of step width and height, and like very much wider space in the stair, on the stair. No, it was very narrow in that case, but it was not so narrow, but maybe more wider. So we could do something if we need to do, if we have more interesting thing to look at. And also I've told you that we could do more studies on different percentage level until exhaustion. So these things.
Even now, like with the data you have, I'm just wondering, like roughly speaking, let's say if you look at the data you have in the field studies plus your first laboratory study, roughly speaking, what percentage of those subjects were above 50 years of age, for example?
I can't say right now.
Like, was it just one? I mean, because like you have range, for example, in one of the studies you have up to age 62. I'm just wondering, was that just one random person at 62 years of age, or was it?
No.
You know, is there a cluster of older people within your data set?
So we had in VO2 data we had 47, for example, in 13th floor, and 29.
Yeah.
So as I said before, during my presentation, that everybody has managed to climb until the end, except one lady. Even though she wasn't old, but she after traveling 21 floor, she quit. Yeah. And also I think everybody has managed. And then it's not that around if you think about 62 step rates, maybe not many. If I cannot say without seeing my data again, but if we look at the standard deviation of the it is 7.1, so standard deviation. So average was about 32 years of age. So even though there are not so many, maybe I don't want to say the number, but because I don't exactly right now don't know. So it would be good to if I can see and tell, but it's
okay. I know, I understand. I'm kind of pushing you here on something that you can't tell me, but like, would there have been more than 3 older people in your whole study?
So I can say the age range from the 31 floor was between 20 and 46. And in 13th floor building, I had 19 and 51 maximum age. So it's a mix of different. I think it's almost similar. It was not even older people in the field study, not more than 51. And we don't expect that performance will be so much different. Also, standard deviation also 9 when the average is 32.5.
Yeah, I guess it would be interesting just to kind of pull out those older people and take a look at their data. Like,
that's why I said in my presentation that it would be good to see different age groups and allowing them to climb until exhaustion. So that would be nice to have data, and then we can probably fire division, if our engineers, architects, they can plan also design the staircase in different way. But I don't know how that will be. But this data may help to design according to the age, and maybe according to BMI would be good. If they have any workload, extra load in their back, some pregnancy cases as well. So yeah.
I'm just I suppose moving to the I think we've ventilated the what piece quite well. We did the why, we did the what. We've touched a little bit in the so what as well, but yeah, let's just, I suppose, move into the so what. Like, so you have characterized, I would say, or described what's happening in different cohorts, in different people, you've put numbers to those experiences, let's say. So what, like, what's the value of doing that?
Pardon, I didn't get that on what did you ask?
So you have gone to great trouble to describe the different levels of oxygen utilization, the different levels of local muscular fatigue, and you've put numbers around them. But what then? Like what can we do with those numbers? What's the point?
I'm really sorry that which one I put the numbers.
I'm sorry. Let me say it again. I'm talking in general terms. Okay.
Oh, okay. Yeah, in that way.
Yeah. I'm talking.
Oh, I got it
general
now.
terms.
Yeah.
Yeah. Like you have all this. You have all these numbers. What do you do with them? How can you interpret them?
Yeah, that I can say. So if you have looked at this percentage level they have reached, because when you did the field study, we didn't know their maximum aerobic capacity level because we randomly picked up the subjects and then tested them when they were ascending. So then we have followed the American College of Sports Medicine data based on VO2 max capacity, and also the another paper, Low et al. From Norwegian population. They have measured more than 1,000 people, I think, and they had oxygen uptake capacity level around 51, age range between 20 to 30. So we have used that parameters, and also we have our student, we have a course called Human Performance in Extreme Environment. So we have used that, their data to see how much percentage of their VO2 uptake reached based on these different values. So we have found about, if I look at the results, if I can set exactly the numbers. So about 91 to 95% they have reached their capacity. So these values, it showed that they have reached 91 to 95% of their capacity level. And in the heart rate point of view, they have reached 83 to 89% of maximum heart rate level, compared to these different standard organization value and the recent Norwegian population, those who were close to the Swedish population fitness level. And if we look at then we didn't have any problem in the laboratory test. We measured their VO2 aerobic capacity, individual VO2 max. So in that case, oxygen uptake was lower compared to their VO2 max. It was, as you have seen, they have reached 44 to 45 milliliter kg per minute, which was about 91 to 97. VO2 90 to 94%, and heart rate was 91 to 97. So they haven't reached to the VO2 max level, because what I have seen, I have collected some. We have asked it immediately after. I haven't reported that in we have asked it, why did you stop? So most of them describe the burning thigh, leg muscle cramped, feeling suffocated, those sort of things. So they couldn't continue. So mainly they complained about the leg muscles. That what we have seen in the results as well from the EMG data, and also finally we had also lactate values as well, which reached 14.2 millimole per liter as well.
How would you convert those findings into a public health recommendation, or in terms of exercise?
Yeah, that's a good question. That's why personally I try always to take the stairs. So as you have mentioned, after climbing a couple of flights, maybe maximum 3 flights, you feel the pounding heart. So that's why you always take the stairs. If you have lift in one side, stairs in one side, you will see everybody is taking the taking the lift instead of taking the stairs. So it's so we can see that stair climbing is very we need very high muscular effort to climb, and also very very demanding task. So this can be used as an exercise point of view. We should always take the stairs to keep ourselves fit. And recently, I think you have seen, I have this Popular Science article in the beginning of this thesis. So I have suggested to climb 18 floors per day in different duration of the day. So 5 floors per time, and 4 times per day. If you climb up and down, that gives at least required exercise. That's what I'm thinking. Those who are for all age groups, maybe it's not maybe applicable for all, but for, if you think about general population overall, to maintain these levels, to gives office workers at least to get the minimum least exercise required per day. But definitely we know that we need to do some physical exercise per day, 30 to 40 minutes. But this gives office worker to maintain their fitness level, and to activate the muscles, leg muscles mainly, and the whole body. And during stair climbing, we can activate most of our body muscles.
Yeah. Okay. I'm conscious now of the time, and I know that my colleagues here would probably want to ask some questions as well. So I'm going to sort of bring us to a close. I've got 1 or 2 more questions. What, in your opinion, is the biggest limitation of this PhD work?
Oh, biggest limitation. I think we have, so if you think about the study point of view, there's of course, we could do it more, extensive way of these things. And I have mentioned some limitations very specifically, but I would, if you ask me to do it again, I will do this kinematics part in a better way, and also we need to set the cameras properly. We need better cameras as well, and also the one most important thing is like we haven't done all the intensities until exhaustion. But you are asking me now challenges. So we haven't. It's a time is another constraints, and also definitely challenges. We don't have enough funding. We got funding for first 2-3 years, but we had to do this for as well with the local funding, in departmental funding wise. So there was not continuous funding for this. There's another challenge to explore these stair ascending physiological constraints and kinesiological constraints. Finding subjects, sometimes it was difficult to find appropriate subjects, and different age groups probably will be challenging if we want to do in future.
One thing we haven't mentioned, and you did call it out in your thesis as a limitation, and that was the fact that in the field studies, the individual's VO2 max wasn't known, and the data had to be sort of back projected onto existing databases. Why was that?
Because we wanted to see which, as you have, I think your question is answering that, because we wanted to know which capacity level they have reached. What is the?
Wait, sorry, but why wasn't the individual's VO2 max undertaken?
No, it was randomly we picked subject through the social media. So we didn't have an opportunity to do the test, because we had to these 3 field tests were 3 parts of 3 places in Sweden. One is Stockholm, Lund, and also 2 is in Stockholm. So we were based in here. So we didn't have enough facilities there to go to Stockholm, and then inviting subjects to come for the VO2 max test, and then plan again do the field test. So that was another thing. And also here in Lund, we didn't also do in that way. So when we started like that randomly, we wanted to see the current capacity what we have. Then we have tried to go back to see how is their fitness right now. So we didn't plan in that way in the beginning. That was another thing you pointed here. But in the field, we had a control here. All the setup was here. Stir machine was here. We bought a new machine here for doing this test, and then we had a control. We could have invited subjects 3 times. Yeah, so they have come here. So it was time was enough to do that, but for the field it was not enough time to do it. And also we plan to do 3 tests as well.
Okay, and so my last question to end on a positive note, because you deserve that. What is the original piece of research you are adding to this field? Like, what is your unique strength here that you've contributed?
Oh, nice question. If you think about personally, I have already answered this, I think. I wanted to learn this method I was fascinated to learn this, to explore human constraints. Positive thing is I have learned what I wanted to learn, these methods at least, and then I can apply these to any field. It can be in sports, ergonomics, working place, anywhere. So this is my personal point of view. And then maybe little contribution to this evacuation field. Now it was not, no one, I haven't seen that it has been shown that showing both oxygen uptake and also leg muscle muscle fatigue consider that can constrain the oxygen uptake earlier than you expect. For example, if you don't reach to your max level. So these sort of small things, there are so many small things I take from this study to move forward for maybe for me, maybe for other who are interested. That could be useful. It can be used. There are so many small things, but effective things are here to take in and to move forward for the future.
Okay, well, thank you very much, Amitava. I think your enthusiasm for this project is very obvious, and you've obviously put a lot of thought into it. I suppose my parting comment to you would be that I think you're sitting on quite a rich data set that could probably be tapped into a bit more than you have, and maybe that's your plan, to continue to analyze and to publish on the data set. But yeah, thank you. Well done.
Thank you so much. I feel I got some very good overview how you think, because when I submitted my papers, I haven't managed to talk someone like that to get a feeling like where should be improved, but only commented what I have done. But now I have got more input. How could I have carried before, and then what should I do? What I haven't done? I think in that point of view, I really appreciate your review on my thesis, and I think that's very nice. I'm very pleased to have your comments, and then it was a nice discussion. Thank you very much.
So thank you both for a very interesting and enlightening discussion. Let's give them some applause. So now we will return to the examination committee for them to ask their questions. So I will start with Professor Ola Eiken.
Okay, can you hear me?
Yes.
Yeah, I am hearing you.
Yes, good. Thank you, Amitava, I enjoyed reading your papers, and thank you for a nice presentation today.
Thank you.
And also Denise, thank you for that opposition. You covered most of the question marks that I had, and which is good, the way it should be. Nevertheless, I'd like to ask a few questions, and using Denise's categorization, I have one biological question, one methodological question, and finally an applied question, if I may. So starting then, on a few places in your thesis, you've used the phrase leg muscle fatigue constrained the subject's cardiorespiratory capacity. So this is, to me, a bit awkward expression, but I think I understand what you mean. But so that there is no misunderstanding, could you please clarify?
Yeah, that's a good point. I also, I think at the end of my understanding, when I was maturing myself up, so I was feeling maybe it's also related to this cardiorespiratory capacity and leg muscle fatigue, because so they are related to each other. And so, but when you talk to the subjects to get the subjective impression, they were always saying this leg fatigue is the most demanding. That was forced them to stop. That was the, if you ask them, we ask it, why did you stop? Then they have said this leg fatigue is the thing that didn't allow to continue. So I was rephrasing that one in taking their comment and then rephrasing in that way to take the load into the cardiorespiratory system. That's why and also as we have, I haven't found so far in my knowledge, I haven't found any study that has measured leg fatigue in this evacuation field. So I was in that way I wanted to emphasize the leg fatigue, which is getting more demand to the cardiorespiratory system to constrain the ascending capacity.
Okay, well, on the same note and the same, or follow up on that, is if you were in this kind of stair climbing capacity, if you will, in these experiments is somehow then limited by the capacity of energy expenditure, or let's say the oxygen utilization in the working muscles.
Yep.
Then we can say that we have several conceivable limiting steps in the chain of respiration, starting with the capacity of the pulmonary ventilation and pulmonary diffusion, and then moving on to the cardiac pumping capacity. And then you have the capacity of the peripheral vasculature, or the vasculature in the working muscles, to accommodate the increased central blood flow. And finally, then you have the peripheral diffusion capacity and the capacity of the contracting muscles to perform aerobic metabolism.
Exactly.
So if these are the classical steps, and if you then say, can you speculate on about which of these steps is the limiting one in this type of exercise, and how you come to this conclusion?
Yeah, the last phase you meant about the peripheral diffusion, and when they also the lactate threshold probably, because we have measured the lactate level, but we didn't measure any like blood flow in the peripheral level, anything. So this utilization of the oxygen when the muscle got fatigued. So there was a limit. There was a limited utilization of oxygen compared to the demand was less. Demand was higher, and then compared to the utilization of oxygen. So that's limited the ascending performance or activity.
Yeah, that's clear. That your oxygen uptake is limiting your performance here. But what is the limiting stage for the oxygen uptake in the chain of respiratory?
Yeah, I was thinking the way I have said in that way. Maybe I have missed one steps in that in between.
Well, probably it's impossible to answer that. I was just a bit intrigued by the that you always talk about the leg muscle fatigue constraining the subject's cardiorespiratory capacity. You get a sneaky suspicion that you think that because you get fatigued in the muscles,
Yep.
it cannot be the central pump or anything else that limits the performance. But you answer that already.
But we haven't. But if you think about we haven't measured anything else. That's why you cannot say something about that in here, because we don't have the evidence that we haven't measured that one. The thing we have measured, I'm answering in that way.
Yes. Okay. How about when you're walking up a staircase, or you're doing rhythmic dynamic exercise in the upright position? Do you know about the blood flow through the contracting muscle or the muscles, the working muscles? When, at what phase are you actually perfusing the muscles? Is it during the contraction phase or the relaxation phase?
So during you mean during dynamic activities? So which
Yes.
phase oxygen is utilizing?
What, no. When are you perfusing the muscle?
Yeah.
At what phase?
During relaxation phase.
That's right. Yes, and so the contraction phase in this kind of exercise is what happens then.
So so oxygen is utilizing, and then we is how to say after during contraction phase the available oxygen is utilizing, and then is during relaxation phase we get the oxygen back and the energy back to prepare for the contraction phase again.
Yes, well, during the contraction phase, there will be an obstruction of blood flow through the muscle. So it has to be during the relaxation phase that you have the blood flow through. And then contraction phase, you're just propulsing the blood upwards. So you have the leg muscle pump, if you will, is working in series with your cardiac pump. So then the question is, do you think that the step frequency has any meaning here or does it affect the oxygen uptake? Can it affect the oxygen uptake?
It's difficult to answer. So it depends also intensity and the duration as well.
Yes.
So which consequence of which point you are thinking? Is it very high intensity activity, or is it low intensity activity and the duration? So I need a scenario to get the question point of view.
Well, I was just speculating that there might be an optimal pace from the peripheral perfusion point of view, so that for instance, if you have a cyclist or a runner, they may choose a pace that is optimal from that point of view, that you allow the muscles to be perfused. But of course, you can't answer this from this data, but maybe you could speculate.
Yeah, I can. Speculation is, I don't believe on my speculation. I have got so many criticism when I was writing the papers, and I have in the beginning I have speculated so many things. Now I have to really stop speculation on
okay.
on
That's prudent enough. I'll move on to the next question then.
I'm sorry,
and then again to these maze diagrams. If I understand, this is a way to determine muscle fatigue by analyzing the EMG amplitudes and the frequency spectrum of the EMG.
Yep.
So that's when you have a concomitant increase in amplitude and a decrease in frequency, this is a marker of muscle fatigue. Is that correct?
Yeah, this when the amplitude is increased and then frequency is decreased or lower frequency, then according to the CIFREC 2009, and then another one was Asplund. So I forgot the other reference I have. So I took this idea, then I brought brought my model, our model to show the EMG in a normal way, easiest way. Yeah, that is right. Amplitude increase and frequency decrease. Is it
okay? So if we go to paper 4, and on page 14, there's a figure 5. Do you have that as a slide? Can you show that?
Paper 4, page 14, or?
That's right. Yes.
Yeah.
Can you put that slide up?
Yeah, sure. I have it in here. Tab. Oops. Oh. Again, the same problem.
Okay, we can do without it.
We're about there. This one. Yeah, this one. Yeah. Then we need to go up. Yeah. Then we have to go up. Yeah, this one. Yeah. Oh, you have to change here as well. Yeah, go back to the next one. So this on the right, the last right one, this step rate 100%. The only one muscle is showing here, vastus lateralis. So
Okay.
Yeah.
Well, anyways, I think we can play it by ear. Everybody has the thesis, I guess.
Yeah.
So then, I might be a bit obtuse here, but when I look at these, the vastus lateralis, the rectus femoris, and the tibialis anterior, there is only one time slot that stands out, being in the fourth quadrangle, and that is at the very beginning, 20 to 40 seconds, or 10 to 20% of your work here. Then you're fatigued, according to this, whereas all the others fall outside of the fatigue quadrangle. So is that, how do you interpret that?
We have pointed this out. It's not that we haven't seen it. It's we have the duration we have recorded. It's sometimes we have tried to cover that all the duration when the subject started climbing, and then sometimes some data are exactly it's sometimes there's some data are not, it's beginning or outside of the recording. Maybe it hasn't been, we didn't try to reduce any data that we had from the stair climbing duration. Probably some data were not relevant to that period. Also the EMG and also the placement of electrodes, something has happened that we couldn't identify this one. We have noticed that, but maybe after a while in the beginning, the data was related to the ascending, and in the beginning maybe some raw values or something, we couldn't identify that one.
Okay, well, I would then go back to Denise was on to this, the validation of this maze diagrams, and if I may be rude, I would say that this, to me, shows that it's not really a reliable marker of local muscle fatigue, because in this exercise they're completely fatigued, I guess, at the very end. Yet you can't see that from the diagram. So I wonder, I don't trust it. Please correct me if I'm wrong.
Yeah, that's you are maybe right. We also thought in that way. It's maybe not. But what I said when I was replying to Dennis, we may need to scrutinize subject by subject, or we need to divide because it's a time normalized duration, whatever the time was there. So we have to be very specific for individual subject point of view, because we have made an average for all subjects here. And also we haven't considered, we have considered all the duration. We have to identify exactly when the climbing was started. But we assumed the duration was recorded was stair ascending according to the file I had, EMG file. But we didn't see any problem. But I don't, because also we have normalized, processed the data based on the same procedure for all subject. We didn't try to do any manual way doing by that. It was done in a MATLAB. So this sort of things, some things we didn't have any under control, everything. So that's why we couldn't
yes,
find
but
out.
still, I mean, when you go to the 90 to 100%, I assume that they are all very close to fatigue here. This is an all-out exercise. So they should be, and then you should, it should stand out like, in the fourth quadrangle there. But it doesn't really. The only one that does is the first time point. So.
Yeah. So yeah, that's you may be right. Also, I may be right, and Dennis may be right. So that's why we need to. We have thought about it. We haven't. We have discussed about it. But we also we have submitted a second division right now, and this second division we haven't got any comment on that at all. So that's also surprising to us, and we haven't gotten so much comments in previous papers as well when we submitted this. So that's how it is. I have proceed on. So so that's what I can say right now.
Okay. So my last question then is, in your thesis here, you repeatedly state that these studies may help the construction builders to design evacuation staircases. For instance, in paper 4, again, that's part of a conclusion. And so then, if we pretend that there was a builder intending to build a shopping mall 100 meters below the surface of the earth, God forbidden, how should I then design the escape to staircase based on your findings?
Good question. So so if you connect, so that is, honestly, that is not my role. I can suggest something that I can show based on my data, that this high you can climb within duration. So that is, this knowledge should be taken by the engineers, planners, architects, and then they should think about how they should plan. But according to, based on this all-out exercise, what I can say, if you have fit subjects like age between 20 to 30, they can manage about 80-90 meter. So there will be no stop within this 3.5 minutes. So you don't need any evacuation. But if we think about different age groups and different body BMI level, and also other cases, disabilities, so we need to consider that. Then we have to make a general evacuation facilities, exit level, heights, and staircase configurations based on that. But that is. But if you, I haven't think about how do you plan, because it was not my duty to do it right now. So
no, I understand that. So I was just curious if you had an idea?
That's what I said. So if the Södermalm, this current, the present under on this work, this deepest subway is working on in Stockholm right now. So if they are not planning any staircase except so many lifts or lifts will be made. So that's why they wanted to avoid long stair flights. So in that case, I think if you ask me directly, as I'm not a planner architect, I would not make more than 30-meter long stair flights, and then each 30-meter we should have different evacuation facilities, resting planes, other facilities for everyone, those who can recover if they need to climb, and then some rescue facilities to have access to the rescuers, so that they can, if they do not manage more than 30 meters, they can take their, they can save some way. So that should be some, that should be arranged, not more than 30 meters from my point of view.
But can't you then just stop at 30 meters in the staircase and recover? Why do you need a plane?
No, that is my thinking, because I wasn't been charged to do that. So that is how I'm thinking. Then that should be, it should be thought by the designer and architects. It's not me who can tell, and they will not take it because I'm not the architect.
Okay, thank you. I'm stopping there.
Yeah, thank you.
Okay, thank you, Ola. Dr. Hilde Freivik, do you have any questions for Amitava?
Yes, I have one short question. And first of all, thank you for a very interesting discussion between Amitava and Denise. It was a pleasure to listening to you, and I enjoyed reading your thesis. And I agree that this is a solid foundation for future research on this topic.
Thank you.
So I just wanted to follow up Aiken's question on practical applications and maybe future research for this, because you have also described in your papers a lot of limitations, both how you can trust the EMG data, how you can use the data into this MACE system, and also you have touched into different age groups, males, females, and so on. But in your introduction, you also talked about making an app that could be used by fire engineers, for example, in helping evacuations. And I was thinking with you have a lot of interesting data, but with the uncertainty in all this study, what would you say is needed to make an app that also would take into account more vulnerable groups like elderly or those with disabilities, that will be those that will go slowest up the stairs? So have you any thoughts about that?
Yeah, only the I was thinking to make an app to get biofeedback in order to prevent injuries. So if someone is able to know that I'm about to reach to my fatigue level by interpreting EMG amplitudes and frequency, so that they can plan their activities, or they can stop. Okay, I'm going to be fatigued, so if I do more, so probably I will be facing an accident. So in that case, they can stop or recovery, so that they can plan their things. Or that's why, at the same time, individual level also, if we get data collected for a lot of population, and the organization level, they can also plan, okay, we should plan work for this work group in that not that long, maybe that duration 20 minutes, 30 minutes at a time, those who are doing repetitive activities. So I was thinking in that way, to prevent injuries and planning work time, work duration for a specific work group. Not only it will not be same work duration for all work groups, and also it should be according to the different work type as well.
Okay, I've just one more question about females and males that you have studied in many of the papers, but in paper 2 you had no you found no differences in between males and females, but they were just as fit. They were young and they were fit. But what do you think? You haven't done this, but maybe you can. I don't. You said you didn't like to speculate, but what if you added the weight of protective clothing, for example, and equipment for these males and females? What do you think you would have expected to see in these results then? Because the females were smaller and lighter, but they had no differences in VO2 parameters.
Yeah, good question. It was interesting to when I did this test experiments, I have found there is not so much difference between this Nordic male, female. The fitness, they're almost equal. So I don't see, but also as you said that these different protective equipments, I think it will be also based on their body size. If you see protective clothing, so there might have some difference, but from the fitness point of view, I don't see in this. If we take only the Nordic population, I don't expect there will be so much difference. At least based on these results, what I have. But it may have. If I think about my origin, so there male female has a huge difference fitness level, because we don't do so much so many equal exercises like male does. So in that case, there may be some difference. We have to think about to whom you are talking, to which people you are thinking about, which target group you are thinking about.
Mm.
So we have to always consider the race, origin, and also definitely the race and origin, also genetical factor as well.
Thank you. And I have no further questions.
Okay, thank you very much.
Hilde. Then I will turn to Associate Professor Stefan Svensson. Do you have a question for Amitava?
I do. Thank you very much.
The mic. Ja. Är den på?
Okay, thank you very much.
I know he has to be last.
I'm on? I am, I think. Will do. Okay, thank you very much. Interesting.
Welcome.
Not really my cup of tea, but still interesting. Very interesting. I was thinking, in your thesis, you're saying that application of the results would be in emergency evacuations as well as during rescue operations. Such situations would, to most people, include some level of stress or otherwise have some kind of psychological impact. So with the risk of going slightly beyond your work here, which means I would like to here to speculate a little bit, and out of curiosity, so how would such psychological impact influence your results? Would it have an impact on stairways, perhaps, floor surfaces, inclinations, flight lengths, distances?
First, psychological impact I expect to how do you perceive the situation, and there again I'm thinking if I'm in such situation, then I will see how I am in a situation. For example, is there any fire? Is there any terror attacks, or what is it? Then I will see. I will check. Is it fight or flights? Then that will be my thing. And then I'll try definitely in any case of like that. Then I will try to take the maximum speed to evacuate, and I'll definitely find the way. And maybe there will be a crowd as well, not only for me to escape. So that also may affect. But if you psychologically, when you say psychologically, then I will consider in that way. those environment and the possibilities and the way which way I should go to, if I can escape, and if there are any hindrances in front of me. So those thinking are coming in my mind. As we haven't managed to do it, I don't know if we can manage to simulate any situation like that. So
I'm thinking in terms of stress. So if you're in a stressful situation, for whatever reason, would that make it possible for me to, in a sense, go beyond what I would normally be able to achieve in terms of walking in stairways?
yeah, it's also individual. From my point of view, how do you perceive? And some people take their stress very easily, some people cannot. So that's what I'm thinking. But I'm not also a psychologist. I cannot exactly tell what's gonna happen. But it would be very nice to, if we can do some test to simulate a real situation, and then to evaluate the behavior. How do you perform? But in this field study, we have tried to see the behavior, and some people we have seen, they thought, okay, it's just a simple test. We just take it easy. Just even they didn't think about they should go quicker. Some people took their steps very easily and took. And sometimes they have rested enough in the between. They knew that it's not a real trial. So that also depends how you perceive the situation. If you think, okay, even it is a test, I'm thinking it's real test. I should go very fast, and how quickly I need to know how quickly I can manage. But people didn't take. That's why you saw the speed curve has plummeted down very sharp decline immediately after ascending. Even they thought I can take the step rate very high in the beginning, then it went down within 20 to 30 within 30 seconds, I think. So it's individual, and human psychology is very interesting to observe. But I don't know if we can manage some study in case of stair ascending evacuation.
Would be interesting to do that.
Sure.
Thank you very much.
You're welcome.
Okay, thank you, Stefan. And then at last we have Professor Christer Malm. You had questions for Amitava as well?
Yes, I do. Can we ask for a 3-minute recess before we go? Can you hear me?
Yeah. You want a 3-minute recess?
Stand up for 2 minutes. So.
Okay. Thank you. I was needed maybe.
Okay.
Can you still hear me? Just checking. I put the headset on.
I can hear you.
We can hear you.
Okay, it's better. The sound is better, I think, with the headset. Okay. So since I'm an exercise physiologist, you need to do some exercise also during your defense.
I also felt that I need to do that. Otherwise, I cannot focus so much.
That's my point.
Yeah.
So whenever you're ready, if you want to run a lap or something, just.
In fact, it would be good if I could have run 5 kilometers now. Then I could come back and do this.
Okay.
Or you can run later.
Yeah.
Can I share my screen?
Sure.
I hope you can see this. Can you see my screen?
Yeah. A firefighter.
Exactly.
And a fire.
I can see that too.
Okay. Are we ready?
Yeah, I'm always ready to escape.
Okay. Yes. So I can really appreciate your work. I was in the same position in 2001 when I defended my thesis. At that time, when I was done, I was called up by the rescue service, what's now MSP, and asked if I could be in charge of developing a new test battery for firefighters. So I did that for about 10 years, and we defended, well, one of my PhD students defended her thesis 2014 on this work. That said, and also that my job, for all those listening, maybe not familiar with a PhD defense, my job is to be a little bit mean, but fair. So I'm not asking questions to be mean, I'm just asking questions to point out some issues. When I defended my thesis, one of my friends ran out because she thought that the opponent was too mean to me. But that's kind of our job.
Yeah.
So here we go. So I think that with that said, there are information in these reports and this thesis and also in these publications that we have out that can help you continue your work. So I would say that the questions I'm going to ask you, the answers are already published in these reports and these scientific papers. Now the MSP, I don't know how your Swedish is.
Det går bra, du kan fråga om
okay.
om
So
du kan.
I'll speak, but the reports are in Swedish.
Yeah.
But I would say that read them.
I haven't read it, so it of course that would be good to.
Yeah, I'm a little bit surprised that you hadn't found them because, and especially since MSP is involved in this, they have the reports since we did the work for them. You talk about limits. What do you mean by limits for physical capacity?
Oh, interesting question. I feel when I can't do any activity, and I thought limit in this stair ascending, how high we can climb, and also the duration.
Right.
So that's what I thought in this stair ascending evacuation case.
Okay, so if I've done some slides here, so bear with me. So you start running up the stairs when there is a fire, exactly, and then the limit that you have talked about is that, or that you also asked or answered to Ola here, that maybe 5 minutes of work is kind of a limiting factor. But so that's the limit. But if you, in your subject cohort, you ran for after 3 minutes, you reach a certain stage, so to speak, right? And they had a VO2 max of around 40 in the tested subject. But what if you had picked a different group of subjects? What had happened then? If you picked less fit older women or more fit cross-country skiers?
Yeah, that would be different. If I take cross-country skiers,
yeah,
probably they will not be in 3 minutes. It's not the limit for them.
Right. No, or they will last longer. They would run further in 3 minutes, right?
Yeah, of course.
So depending on your VO2 max, you'll run further.
According to the VO2, yeah, of course.
Right. So the question, and where would you put the doors? I mean, you said you weren't a designer, but Ola asked, where would you put the escape doors?
Exactly.
With this in mind.
So if you, I think I have already answered, or I don't know if I haven't. So if you think about the fit group I had last phase of the study, when I wanted to see how long they can manage on that specific stair machine we had in our lab. So in that machine they have managed 3.5 minutes. So
at a certain pace.
Yeah, and in that 3.5 minutes they have managed to climb about 95 meters. So there would not be any problem. So if there are people like this group, this fit group people, they can manage about 80-90 meter without any problem.
Right. But that's but that's what I mean when you say limits. Then, if you talk about the limits, if you set the limit, I mean, I'm thinking from the perspective of MSB or the fire engineers designing this. They need to put the escape door at a certain spot. They need to put it at 30 meters or 50 meters or whatever. And you said you wouldn't put it more than 30 meters, but of course. That will also then if you have a normal distribution of your population, even if you put it 30 meters, some people will not make it if you have 3 minutes. So I mean, is the limit that you talk about, is it the VO2 max limit or is it the time limit from the rescue service? How long will it take for people? How much time do they have to get out of the building? What's the limit?
Exactly. Then I would not say this right now. I need several studies to do based on different age groups, different BMI group, and then still I'm not covering the disabilities, pregnancies, children. So if you ask me honestly, then there is no limit.
Exactly.
In terms of different age groups, and there is no solution. We have to do something what is acceptable, what we can do to cover most of the groups, almost every groups, age groups, BMI groups, children, and so there is no. We don't see any. I don't see, if you think in that way, I don't see any limit.
No, exactly, because we try to get a limit for firefighters. Because they said, what is the needed VO2 max for a firefighter? Well, it depends on how fast they're going to do the work, and it depends on how hard they're going to work and for how long. And it all interacts. So when you talk about limits in your thesis, I was a little bit confused because I couldn't find any limits.
Yeah, me neither. But based on this study, we could say that that group of population, and it is generalized to that age groups. And if you are fit, then you can climb that long, and your VO2 highest will be reaching around 44-45 milliliter kg per minute. That is continuous work, constant pace. So there is no different activities involved here, only stair climbing.
So in that case, the limit is that in your group that had a VO2 max of 40, they will climb, what did you say, 90 meters in 3 minutes?
Yeah.
So that's kind of the limit for that age group.
Yeah.
But how do you use that data to design an escape? Because that only applies for that specific group tested. So you say you want to test more people, but you need. My point is that you need to ask the MSB or the rescue service what is the acceptable, if you be crude, what's the acceptable death rate? How many can we sacrifice? Because if you put the door at 20 meters, most people are going to make it. If you put it at 40, less people are going to make it out in case of a fire. So my point is that the limit here is you have to be careful when you talk about limits in this situation, because a VO2 max is the limiting physical work capacity of that studied group. It's not the limit of how quickly you get out of the subway or the building.
Yeah, that's what I think I have said. Duration limit 2 to 6 minutes if you climb at maximum level, and if you are fit, based on this population.
Now you're saying that MSB gave you a 6-minute limit, that everybody has to be out of the building in 6 minutes.
Yeah, if you are a fit person, then based on the subjects what I had, so that could be 2 to 6 minutes if you climb at maximum effort.
Okay. Well, but okay. We'll move on. So and the other thing that you have to consider this that all measurements that you do has an error. I'll get back to that. We can skip this. So then the other thing that we'll get into is that you talk about VO2 max as one limiting factor and EMG. And I think you talked about this other I know Ola asked about that. What are other limiting factors for performance here? But I think we discussed that already, so we can maybe skip that. Maybe you should talk about anaerobic capacities and all the issues that Ola talked about. Not to mention what you also mentioned, the psychological factors. So that is VO2 is and even EMG is, it's only a part, and we'll come back to that. How big part of the performance is really VO2 here? Yep. What is it? 20% or 80 or 90% of a performance? We can skip that. So, and my suggestion, and there are other ways to set limits. You can actually calculate this. There are ways to estimate limits within statistics, statistical limits that you can look into.
Where I can find that one? That
you use I mean, there are statistical methods.
Okay,
you said SPSS.
Yeah.
I mean, this is just from one statistical software. This control chart made an example of some of your data that okay, so where are the limits for speed and how, what's the percentage error and so on. There's a deeper statistical analysis that you can make here. And also, yeah.
Which data set you have presented here?
I have asked for your supervisor for data set from your first study.
Okay, that one. Okay. Yeah.
So this is data from your first study.
Okay, I see.
So that's what I mean, that you have to consider other factors. So I'm lecturing more than asking here, but you have to consider other factors than just VO2 when you talk about these limits and define what you mean by limits. So my next question is then, you talk about correlation. What do you mean? And then what do you mean by correlation? This is also from that first data. You had other, we've looked at other line graphs before. This is the VO2 and heart rate. So I'm going to move on to next. So when I look, do correlations, it's like in this case a regression model, that there's a correlation between heart rate and VO2. Okay. That to me is a correlation, right?
Yeah.
And in this paper, you talk about the correlation between fatigue and EMG signal, basically.
Yeah, this one is ascending speed, or ascending speed and EMG amplitudes, I think. Yeah.
And would you say that there is a correlation then between the ascending speed and EMG?
We see a relation here, a relationship between the ascending speeds and amplitudes here.
Right. And this you tested by the Friedman test.
Yeah.
Okay. So what does the Friedman?
Sorry. We have just wanted to see that if the differences from 10 to 100% level is this significant or not. That we have done. That is not the Friedman test correlation.
Okay, but you say here that it's according to the Friedman analysis.
This is the test we wanted to see if these changes from 10 to 100% are significant between these values.
Right. But if you read what the Friedman test really does, it compares groups over time, right?
Yeah, that's the groups. We have 10, 20.
But those are the same subjects at different time points.
Yeah.
The groups are if you had men and women.
Yep.
So that would compare, or you could, if the red lines were men and blue lines were women, you could compare men and women over time with the Friedman. So I think you need to look into statistics here.
Yeah, we thought this 10 to 20, 30, 40, we have different set of subjects. We wanted to see the difference between 10 to 20 all the way up to 100% time duration.
But is it not the same subjects you've tested at different intensities?
Yeah, this is the same subject, it's true.
Right. But the Friedman analysis difference between groups, not within groups.
So this is it is Friedman test can be done for 3 or more conditions, right?
Yeah. But if I understand, I'm not a statistician, but if I understand this correctly, the Friedman is between groups. This is over time. You can do group difference between groups over time, but you're not comparing groups. You're comparing just the same subjects over time.
Yeah, I have followed the chart from one of the statistics books. It's Friedman test can be done for the same subject and
Okay.
matched design, and then when you have 3 or more conditions, then I have followed that one to do the statistics.
All right, we'll move on. But and then you because if you look at the correlation, I think also the maze squares that you talked about, if you take the data that you have here and you plot it like I have in the upper right hand corner, and then you add the standard deviation, I think you can answer Ola's question.
Yeah.
Why was there differences in the maze result? Can you see that the reason here?
Yeah, that when we have seen this one, and then when we had this quite standard deviation bar, and then we had to consider this EMG. EMG data is varying between subjects and individual subjects events, and we had to skip that one and just put the plain lines without having disturbing the figure so much. So
but you use the EMG in the maze chart, right? Right. So I think you have to look into this variation plot, because then this I can send this to you. I mean the upper right hand corner then is the correlation between speed and EMG signal, and it's not correlated. And the lower hand is repeated measurement over time with the same data set and with the standard deviations noted, right? And then you can see that the R squared, the change over time here is not significant because of the high variation in data. Yeah. So I think you have to take a closer look at the statistics here. I'm going to skip through some stuff. We're running late, but I did a lot of these when you write the correlations, and I have a hard time finding these correlations. So my suggestion here is that you maybe look at this with the statistician. Have you consulted a statistician in this work?
I have taken couple of courses, and then my supervisors helped me to do this. Yeah. Right. So when I have done by myself, then I discussed with them. Yeah. And also we went through this submission procedure, several revisions. Yeah. And then it went through. So.
Right. So because the other thing that surprised me here is that if you actually do then compare the two groups that you have, if I merge the data from the 13 and 31 floor buildings, and you look at the VO2 speed and I took some examples of the EMG data. Is there a difference between, why is there not a difference between the buildings? They ran 13 or 31 floors. Shouldn't that be different?
Yeah. So you compared here two buildings, and which data it's very small here. I can see.
Okay, it's the top one is VO2. Yeah. And then you have speed, and then you have vastus lateralis, MDF, and RMS data. But there is no difference in work intensity or speed or EMG signal between the buildings. Exactly. And I don't get it, because they ran for different lengths of time.
Yeah, but still they have chosen their own speed, and they have planned to reach the top. So that's why they have adapted their speed in their way, so that they can reach to the top. So that's why maybe it's they have avoided being fatigued so much or exhausted, so that they can continue until the end.
But what was the time for the 31 and 13th floor building?
3 minutes and 8 minutes.
Okay, so if you knew that they knew they were going to run for 8 minutes or 31 floors, they still picked the same pace as when they were running for 13 floors.
If I check the speed again carefully, I can say exactly the speed was the same or not.
It's right here. It's 1 meters per second in average, both groups.
Yeah, yeah. So
it's the second from the top.
So I think what I have seen is still they could have gone another 6-7 minutes, maybe until 15 minutes. They will not be exhausted if they can. If the building is 200 meter almost, maybe probably they could have continued.
How would you run if there was a fire at the bottom of the building? How would you run?
Yeah, that's interesting. So it's as I said, to answer to one question from Stefan, one of the examination committee member here. So it depends how you perceive, and also if there is no hindrances in front of you, and then if you are fit or not, and then how you psychologically strong or not. So all these factors will be coming into your how you decide, how you choose your speed.
Yeah. Okay, so we move on. I have some more statistics. I'm not gonna. So then, can you think of another way? Because Denise was suggesting also the same thing, that you have so much data collected. You have a tremendous. I mean, I can really appreciate the effort. I do a lot of exercise testing myself up in Umeå here, and I can really appreciate the effort of testing. It must be over 100 subjects that you have.
Yeah, altogether.
And then you said you did not consult a statistician, like a professional statistician.
Not really, no.
Okay. So maybe it's hard for you to answer this question then, if you can think of a different way of analyzing data when you have so much data.
Yeah, it would be great if we could do more analysis based on the data we already have, if we can find something else. But I don't know if the statistics always saying right things. I sometimes got different things and different results, because I also tried mixed model analysis. Then I have considered a little bit that time. Then he also didn't find so much interesting thing. Maybe I was not so good at that time. I'm not still. I know very little about statistics right now, but in that period also he found, okay, maybe it's not good to show in that way or not. So then we skipped and then choose the easiest way to represent the data we have right now.
Right. So since you have so much data, you have so many variables.
Yeah.
There's a whole field of statistics called multivariate statistics.
Yeah.
And the thesis that Ann-Sofie Lindberg wrote, and the couple of publications we have in +1 uses this approach to analyze also performance data in firefighters.
Yeah, I have seen these two papers.
Yeah. So if I pull your data in to this to a multivariate statistical model, you can find a lot of interesting things. So for example, in the left graph here, you can see the number 10 here is that the correlation between different EMG measurements is completely related to the subject, not to how hard they have worked. The right-hand side shows the same thing with it's called a PCA plot, partial principal component analysis, which reduces dimension in the data set. And it could also see that the number 10 subject here completely stands out. And down here to the right, you have number 7. To the left, you have number 3. So the EMG data has absolutely nothing to do with the work intensity. It only depends on the subject.
Yep. That's what I replied. Sorry.
Yeah, no, go ahead.
I said that's what I said. It should be EMG data should be treated individual wise. It cannot be. But we wanted to see if there is any pattern, if we can find any pattern if we look at the amplitude wise for all subjects. So, but I knew that this EMG should be always individual wise
right. But that's not how you present it. You present it as a mean average of groups.
That's try to find an amplitude pattern if we can find it.
Yeah, but this quickly tells you that there isn't one. So these are the multi, and you can. I was just exemplifying that, because the other thing that my question was that you're trying to have a different. Oh, sorry, I'm going to go here. You have also tried. You say that you want to say something about other groups. That is, you predict. You write the word predict sometimes. Do you know the difference between a correlation and a prediction? From a statistical point, you use the word prediction in your thesis.
Yeah, so to predict and estimate something, or in correlation is there a relationship? What I feel right now, I can answer. So
Well,
you said which data you are talking about? This one is.
No, I was just in general. What is if you know the difference between a prediction and a correlation or regression? I mean, from a statistical point of view, there's a difference between the two terms.
So if you find any correlation, then you can use that one to predict something.
If the data is valid.
Valid, yeah, exactly, yeah.
Yeah, but then you have to validate the models.
Yes.
And if you take I just took some examples here that you find the variation in your data set on the left hand, and then on the middle side, the regression prediction model says that 70%, 0.7 here is what you can, the variation in data set can be explained to 70%. And if you do a prediction model that you take out some of the data and try to predict that it fits the model, then you can do this to 0.5%, so slightly lower, and the right hand says that it's a valid model. But I haven't seen any of this analysis in your data that you have done validation of the models.
No, we haven't done that.
Right.
Yeah.
So okay, because you said you wanted to predict things, and then I couldn't find validation analysis. So I was a little bit confused.
Only we have the model we have made to estimate the step rate. Then we have calculated the step rate for another groups to if we see any pattern for oxygen uptake, so higher oxygen uptake for higher step rate. That's we saw as a validation. So we saw.
Right, but did you expect something else than a higher VO2 with higher step rate? Could it be any other way?
No, honestly, I haven't thought about that.
Okay.
Oh.
So the other thing that you could do with this, you can also rank the what I did in this model. I ranked the importance of the variables included, right? So you have the highest ranked, the most important variables in this data for separating is some of the EMG signals, while VO2 max and heart rate really isn't, that they're not variables important for these models. So that's what I mean. You can find out what's difference between the two groups. You can see that the subject 10 and subject 2 differ, and then you can get a ranking of what is the difference between the subjects. My point is that there's so much more to be done with your data.
Excuse me, Chris.
Yep.
Do you have concrete questions? Because I think that a lot of the discussion you could maybe pass on to Amitava.
I am
at
done.
a later mod.
I'm done. Thank you.
Yeah. Okay. Thank you.
Thank you, Mom.
So everybody in the examination committee has asked their questions and hopefully got their answers. So we ask the public if you have any questions. There's one question on YouTube, or from Magali, who's on YouTube, but actually she says if the question hasn't been answered yet, and it actually has.
Okay.
So you're off the hook.
Great.
I think you have defended your thesis for quite a long time now, and very well done. And if there are no questions left, okay, then I would like to end this Defension Act. So thank you, everybody that has been involved. Now what will be happening now is that I would like to ask the members of the examination board, both on Zoom and in real life, which is growing into a very popular term right now, to follow me, and the supervisors also, and the opponent. And the rest of you can mingle for a while outside, and there will be refreshments here in a little while. And then we will all meet down here again to hear the verdict. Okay, thank you.